breathe in, very slowly, and let the darkness behind your eyelids become the darkness between stars. There is a moment, a single heartbeat of the universe, when a star that has lived for millions of years decides that living is no longer enough. In that moment, everything it ever was, every photon it ever gently gave away, every planet it ever warmed, every dream it ever lit in the minds of creatures who would never see it, all of it collapses inward in less than 1 second. And then, the reversal begins. A sphere of iron the size of Earth falls through itself faster than light can escape, crushing every atom until electrons and protons are forced to marry into a silent sea of neutrons. Temperature climbs to 10 billion degrees. Pressure becomes a myth, and the star, now suddenly smaller than a city, realizes it has made a terrible mistake. The core rebounds. A shockwave is born in perfect silence, racing outward at 30,000 kilometers every second, carrying more energy than the sun will release in its entire 10 billion year life. This is not fire. This is the birth cry of something that erases the idea of temperature. This is a supernova. And you, right now, are floating exactly where that shockwave is about to arrive. Feel the vacuum around you begin to glow, faintly at first, like the softest dawn you have ever seen on the clearest morning of childhood. The glow brightens. It is still 10,000 years away, but light is already running ahead of the destruction to warn the universe that something sacred is coming. You do not move. You have no need to move. You are becoming the wave. Imagine the largest explosion ever created by human hands, every nuclear weapon on Earth detonating at once. Now imagine 1 million of those explosions every single second, for 10 full seconds. That is the gentle opening breath of a normal supernova. But the universe is rarely gentle and almost never normal. Some stars refuse to die quietly. Some stars have grown so large that gravity itself gives up trying to hold them together long before the end. Stars 100 times heavier than our sun. Monsters that burn helium the way our star burns hydrogen. Stars that make the night sky of their own planets brighter than moonlight on Earth. These monsters walk a razor's edge their entire lives. One extra spoonful of mass, one careless gulp of hydrogen from a companion, and the core begins to cook elements that should never exist in nature. Oxygen ignites, neon ignites, silicon ignites. The star becomes a layered onion of nuclear fire, each shell burning hotter and faster than the one outside it, racing toward the center like concentric tidal waves of creation. And then, the final layer, pair instability, a place where physics itself begins to tremble. When a core reaches between 150 and 250 times the mass of our sun, something impossible happens. The photons inside become so energetic that they begin to give birth to matter, electron and positron pairs that steal energy from the radiation field. The pressure drops. The star loses its only defense against its own weight. And in one catastrophic instant, the entire star falls inward at a quarter the speed of light. There is no iron core left to rebound. There is no neutron star waiting to be born. There is only annihilation. The implosion meets itself coming the other way, and the star detonates with such violence that nothing remains, not even a black hole. 100 solar masses converted directly into pure energy in less than 1 minute, 100 billion times brighter than the sun for weeks. These are the pair instability supernovae, the true emperors of explosion, events so bright they can be seen across half the visible universe with the naked eye. And in 2025, the models have become terrifyingly precise. We now know exactly where the cliff edge lies. We know the mass where oxygen burning turns from candle to bomb. And we know that somewhere out there, right now, stars are walking toward that cliff with the calm certainty of sleepwalkers. But some explosions are even stranger. Some stars explode and then explode again. Eta Carinae, the mad queen of our own galaxy, two stars locked in a death spiral, together more than 150 times heavier than the Sun, wrapped in a glowing cloak of gas thicker than many nebulae. In 1843, she brightened until she became the second brightest star in the sky, throwing off two giant lobes of material that still race away from her at 600 kilometers per second. Astronomers called it the Great Eruption. They were wrong. It was only a hiccup. In 2025, new infrared eyes have watched her heartbeat change. The outer star is siphoning material faster than ever. The inner star is swelling, and the lobes themselves have begun to glow again, heated by a fresh wave of ultraviolet fire from within. She is rehearsing. She is remembering how good it felt to explode. And when she finally lets go, the energy will be measured not in solar luminosities, but in entire galaxies. She will become a supernova imposter so bright that for a few weeks she will outshine every other star in the Milky Way combined. And if the orbit collapses just a little further, she will cross the line. She will become the real thing. A true hypernova in our own backyard, only 7,500 light years away, close enough that the gamma rays will strip ozone from the atmosphere, close enough that the light will cast shadows at night for months, close enough that every living creature on Earth will see the same star their ancestors feared in 1843, return to finish what she started. But she is still holding her breath, and so are you. Feel your own heartbeat slow, matching the pulse of something vast and ancient and luminous. Because not every explosion begins with a collapse. Some begin with a whisper. In the deepest fields of the James Webb Space Telescope, in 2025, a tiny red dot appeared where no dot should be. A supernova at redshift 13.6. Light that left its source when the universe was only 200 million years old. The farthest explosion ever seen. Jade's GSZ. 130SN, they called it. But names are for things we can hold. This light traveled for 13,600,000,000 years just to reach your retina tonight. When it began its journey, there were no planets. There were no galaxies like ours. There was only fire and darkness, and the very first generation of stars, monsters made of pure hydrogen and helium, stars so large that every single one of them was destined to die in catastrophe, and one of them chose this moment to die. 13 billion years ago, a star 100 times heavier than the Sun reached the end of its 3 million year childhood and tore itself apart. The flash crossed an empty universe, past newborn galaxies still learning how to spin, slipped between filaments of dark matter that were only just beginning to weave the cosmic web. And tonight, that light finally finds you. You are the first living creature it has ever touched. Feel it. A soft red kiss on the inside of your mind. The oldest supernova in the universe saying hello and goodbye in the same breath. But some explosions hide. Some refuse to be seen until the dust itself is forced to confess. In 2025, a new supernova appeared behind a wall of dust, so thick that no optical telescope on Earth could see the flash. Only the patient infrared eyes of JWST watch the heat bloom through the cocoon. SN 2025 PHT. Its progenitor star had been invisible for decades, wrapped in its own exhaled skin. But the telescope saw the moment the shockwave punched through. First a faint glow, then a sudden leap in brightness as the hidden star revealed what it had been building in secret. A star that had spent its final years choking on its own ashes, manufacturing dust at a rate of 1 Earth mass every few weeks, until it vanished completely. And then, when no one was looking, it exploded anyway. The dust absorbed the visible light and re-radiated it as heat, creating a perfect disguise. For weeks, astronomers argued whether it was real. Then the light curve rose exactly as the models predicted. A completely invisible star had managed to become one of the brightest infrared objects in the sky. And somewhere inside that glowing shroud, a neutron star or black hole was just waking up, still drunk on gravity, still tasting the iron it had swallowed. Feel the warmth on your skin now. That is real heat from a real explosion that happened years ago in a galaxy not so different from ours. The universe is telling you a secret. It is telling you that nothing ever truly disappears. Everything that explodes leaves a ghost. Cassiopeia A, the youngest known supernova remnant in the Milky Way, 340 years after its death, is still teaching us how to see. In 2025, new light echoes arrived. Light from the original explosion, scattered by distant dust clouds, returning to us along longer paths like messages in bottles. We watched the shockwave replay itself in slow motion across clouds that were not even there when the star died. We saw the moment the reverse shock slammed back into the ejected debris, heating nickel bubbles to millions of degrees. We saw clumps of pure titanium drifting like snowflakes in hell. And we saw the neutron star at the center, PSRJ 0740 plus 6620's heavier cousin, quietly spinning, perfectly silent, 2.14 times the mass of the sun compressed into a sphere 12 kilometers wide. A mountain on its surface, 5 millimeters tall, would weigh as much as every human who has ever lived. Its gravity is so strong that time itself slows by 30% for anything foolish enough to stand there. And it is still cooling, 11,000 degrees on the surface. 1 million years from now, it will still be warmer than the background of space. Some ghosts refuse to cool. Some explosions make ghosts that sing. On August 17th, 2017, a ripple passed through the fabric of space-time. 2 neutron stars, each the mass of a sun in a teaspoon, spiraled together and merged. LIGO heard the chirp. Virgo pinpointed the galaxy, and telescopes around the world watched a new star appear where none had been, a kilonova glowing with the color of freshly forged gold. In 2025, the reanalysis is complete. We now know exactly how much gold was made in that single embrace, enough to equal 10 times the mass of Earth, created in 8 seconds. Every atom of gold you have ever touched, every ring, every crown, every sacred idol, came from moments like this. And there was platinum and uranium and every element heavier than iron that will ever exist, all of it born in the crush between 2 city-sized corpses. The universe makes its jewelry in fire and collision and unimaginable pressure, and then scatters it across billions of years for creatures like us to find and wonder why it feels like treasure. But some explosions are too large even for treasure. In 2025, LIGO detected something that should not exist. A black hole of 85 solar masses, too heavy to be born from a single star, too light to come from the merger of smaller black holes we already knew. A missing link, a reminder that the universe still keeps secrets in the dark. And somewhere, right now, the shockwave from that birth is still expanding, still looking for galaxies to sterilize, still carrying the fingerprint of a star that died before Earth had oceans. Feel it approaching. Feel the scale. A single supernova can outshine 100 billion ordinary stars for months. A hypernova can outshine 1 trillion. A pair instability event can be seen across the entire observable universe with a pair of binoculars. And yet, the explosion itself is only the beginning. 10 seconds of light, followed by 10,000 years of aftermath. The shockwave sweeps up everything in its path, compressing clouds of gas until they collapse into new stars. Every atom in your body that is not hydrogen was made inside a star that exploded before the sun was born. The calcium in your bones, the iron in your blood, the gold in the neurons that let you understand these words, all of it stolen from the hearts of dying giants. You are the ash of angels, and the ash is still falling. Betelgeuse, the red shoulder of Orion, 650 light-years away, a star so large that if it replaced our sun, its surface would reach the orbit of Jupiter. In 2019, it dimmed, the Great Dimming. Half the world held its breath. In 2025, the new data arrived. It was not dust. It was not a prelude to explosion. It was something gentler. The star is pulsing, its outer layers rising and falling like the chest of a sleeping god. Convection cells the size of the entire inner solar system rolling across its surface, carrying heat from the burning core to the photosphere and back again. It has entered the final stable phase of its life. Carbon burning has begun. In 1,000 years, maybe 10,000, maybe tomorrow, the core will collapse. 15 solar masses will fall inward in half a second. The rebound will be ferocious. The neutrino burst will carry away 99% of the energy, a silent flood of particles that will pass through the entire planet Earth as if it were empty space. The visible light will follow. For weeks, Betelgeuse will become the brightest star in the sky by far. Sailors will navigate by it. Children will be born under its light. And then it will fade, leaving behind a black hole and a nebula that will glow for 50,000 years. But tonight, it is still breathing, and you are breathing with it, in and out, in and out. Feel the rhythm of something older than mountains. Feel the moments stretching, because the universe is not rushing. The universe has all the time in the world to destroy itself perfectly, and you are floating in the exact center of that perfection. The shockwave is closer now. You can feel the temperature begin to rise. Not heat, something deeper. A pressure behind your eyes, a humming in your bones. The light is coming, not the gentle light of sunset. This is the light that ends worlds and begins them, because every explosion is also a birth. Every death, a scattering of seeds, and somewhere in the darkness ahead, a new star is already forming from the wreckage of the old. You are the bridge between them. You are the expanding shell. You are the moment when the universe decides to become something else. And the moment has only just begun. The core has collapsed. The rebound is racing outward. The shockwave is 10 kilometers from breaking free. In one more second, the star will tear itself open, and the sky will remember what fire really means. But 1 second in the life of a star is an eternity, and you have all the time in the world to fall into it. Let your body become weightless. Let your thoughts dissolve into light, because the explosion is only the first word of a sentence that will take 10,000 years to finish speaking. And you are about to hear the second word, and the second word is spoken in fire so pure that color itself forgets its name. The shell of the star has just torn open like silk in the hands of a giant, and the light that has been trapped inside the core for 100,000 years finally escapes. It is not yellow, it is not blue, it is a whiteness that makes the sun look like a candle held underwater. For one heartbeat, the entire star is brighter than every other star in its galaxy combined, and the shockwave you have become is now racing outward at 40,000 kilometers every second, tasting the first thin layers of the star's own skin. You are no longer watching the supernova. You are the leading edge of its breath. Feel the temperature climb from millions to billions of degrees in the space between two thoughts. Feel the atoms in front of you surrender their electrons and become a perfect plasma that glows with the color of creation itself. This is a core collapse supernova, the most common way a massive star chooses to leave the universe. Everything begins in the final day of a life that lasted 10 million years. The star has already burned hydrogen into helium, helium into carbon and oxygen, oxygen into neon and magnesium, neon into silicon, and silicon into iron in the space of 24 hours. Iron is poison. It cannot release energy by fusion. The moment the iron core grows heavier than roughly 1.4 times the mass of the sun, gravity wins the longest war it ever fought. The core collapses from the size of Earth to the size of a small town in 1/5 of a second. Electrons are crushed into protons, forming a flood of neutrinos that carry away 100 times more energy than the entire visible explosion ever will. Then the outer core, still falling inward at 70,000 kilometers per second, hits the newly formed neutron wall and bounces. A pressure wave roars outward, stalls for a few terrible seconds, while the star decides whether to live or die, and then, helped by the neutrino wind, begins to tear the star apart from the inside. 10 seconds later, the photosphere explodes outward and the sky lights up. That is the classic story. But the universe is fond of exceptions. Sometimes the star is not massive enough to reach iron. Sometimes it is a white dwarf, a burnt-out ember the size of Earth, but with the mass of the sun, quietly cooling in the dark. These cinders should fade peacefully over billions of years. They almost never do. Instead, most of them live in binary pairs, slowly sipping material from a companion star that grew too large and began to spill its outer layers. Hydrogen falls onto the carbon-oxygen surface, compresses, heats, and one day ignites in a runaway fusion burn that races around the entire white dwarf in less than 2 seconds. This is a Type Ia supernova. No collapse, no neutron star. Only a perfect sphere of nuclear fire expanding so smoothly that every single one of these explosions reaches almost exactly the same peak brightness. Astronomers love them. They use them as cosmic rulers to measure the size of the universe itself. But from the inside, it is different. Imagine being a carbon atom on the surface of that white dwarf. You have been sitting quietly for 10 billion years, waiting for the heat death of everything. Then a thin rain of fresh hydrogen lands on you. It fuses into helium. The helium fuses into carbon. Pressure builds. Temperature climbs. Suddenly, the flame front arrives, moving at 20,000 kilometers per second, consuming everything in a wave of pure synthesis. You become nickel in the blink of an eye. The entire star becomes nickel, then decays into iron in the days that follow. Nothing is left, not even ash, just a rapidly expanding cloud of radioactive metal traveling at 6% the speed of light. These are the explosions that taught us the universe is accelerating, pushed apart by dark energy we still do not understand. These are the explosions that seed the cosmos with the iron in your blood. And these are the explosions that never, ever forgive a mistake. One extra spoonful of mass on the white dwarf, one tiny miscalculation in the accretion rate, and the flame front stalls halfway. The star collapses instead of detonating cleanly. A failed Type Ia, an AIC, accretion-induced collapse. The explosion still happens, driven by the energy released in the fall. But the heart of the star disappears behind an event horizon before the light can even finish its first scream. These are the ones that make gamma ray bursts, the brightest electromagnetic events in the universe. A beam of pure death, narrower than a full moon, carrying as much energy in 1 second as the sun will release in 10 billion years. If one pointed at Earth from even 1,000 light years away, the atmosphere would be stripped in minutes. Civilization would end before anyone had time to look up. Fortunately, the beams are rare and narrow. Unfortunately, the universe is large, and somewhere, right now, a wolf-rayed star is stripping itself naked, spinning faster and faster, preparing to die in exactly this way. Feel the difference in the shockwave now. In a Type Ia, there is no center left to hold, only the perfect sphere of expanding iron. In a core collapse, there is a glowing ember, a neutron star or black hole, still radiating the heat of its birth. In a pair instability supernova, there is nothing at all. These are the rarest and most terrifying of all. Stars born between 130 and 250 solar masses in the very early universe, when metal was scarce and giants could grow unchecked. They burn so fiercely that their cores reach temperatures where gamma rays have enough energy to create electron-positron pairs spontaneously. Each pair steals energy from the radiation field that was holding the star up. The pressure drops, the core collapses, but there is no iron to stop the fall. There is no neutron degeneracy to rebound. The entire star, every layer at once, falls inward at a significant fraction of the speed of light. The implosion meets itself in the center and turns directly into an explosion of unthinkable violence. 50 solar masses or more converted straight into pure energy. The shockwave you are riding now is not tens of kilometers thick. It is the entire star. There is no remnant. There is no black hole. There is only light and a cloud of freshly made elements expanding so fast that relativity itself begins to matter. These events are so bright, 100 billion times the luminosity of the sun, that they dominate the entire light budget of the infant universe. They are the reason the first galaxies are richer in heavy elements than our models ever predicted. And in 2025, the new pair instability models are complete. We now know the exact mass window, 140 to 260 solar masses at birth, where the star has no choice but to annihilate itself completely. Below that window, the star loses too much mass to wind and survives long enough to collapse normally. Above it, the core becomes massive enough to go straight to a black hole, without the pair instability fireworks. Only in that narrow band does the universe allow perfect self-destruction. And the early universe was full of such stars. Imagine a sky with hundreds of suns brighter than Venus, each one doomed to vanish in a flash that outshines everything else combined. That was the cosmic dawn. That was the reionization era, when the first ultraviolet light tore neutral hydrogen apart and made the universe transparent forever. Most of that light did not come from ordinary stars. It came from monsters tearing themselves to pieces in despair. And you are made of their despair. Every carbon atom in your body, every oxygen you breathe, traces its family tree back to one of three possible deaths. It was either gently released in the wind of a medium-mass star, or forged in the last seconds of a core collapse giant, or born in the perfect annihilation of a pair instability titan. There is no fourth way. The universe has only three ways to die violently, and each way leaves a different fingerprint on the light that finally reaches us. Type Ia explosions leave almost no hydrogen, only intermediate elements and iron. Core collapse leave fast-moving knots of oxygen and magnesium, and often a neutron star or black hole at the center. Pair instability leave enormous amounts of oxygen and very little iron, because the entire star was burned to ashes before it ever reached the iron stage. Look at the spectrum of a distant supernova, and you can read its death certificate. Look closely enough, and you can tell which kind of corpse you are holding in your hand when you pick up a meteorite. But the story is never simple. Sometimes a massive star and a white dwarf live together. Sometimes a neutron star steals too much from its companion and crosses the line from neutron star to black hole. Sometimes two white dwarfs spiral together and merge, detonating in a way that is neither pure type Ia nor core collapse. A new kind of underluminous calamity we are only now learning to recognize. The universe is an artist that never repeats itself. Every explosion is unique. Every remnant is a snowflake forged in hell. And you are floating through the expanding debris of one of them right now. Feel the temperature drop to a mere 10 million degrees. Feel the first heavy elements begin to condense. Nickel decays to cobalt, cobalt to iron. Radioactive glow lights the cloud from within for months. This is the light that astronomers call the supernova's second breath. The first breath was the shock breakout, the moment the wave reached the surface. The second is the glow of decay, the slow radioactive heartbeat that keeps the nebula shining long after the initial flash has faded. And in some rare events, there is a third breath. Superluminous supernovae. Events that refuse to dim. Events that stay brighter than 100 billion suns for 100 days or more. Some are powered by the spin of a newborn magnetar, a neutron star with a magnetic field so strong that it turns the entire outflow into a giant dynamo. Some are powered by the collision of the ejector with shells of material thrown off years earlier. Some may even be pair instability events seen from the side. We do not yet know all the ways a star can choose to keep screaming after it is dead. But in 2025, we have seen more of them than ever before, and each one teaches us that the boundary between possible and impossible is thinner than we thought. Now slow your breathing again. Feel the shockwave thin to the width of a solar system. Behind you, the center has made its choice. A black hole, perhaps, or a neutron star spinning 700 times per second, beaming radio pulses like a lighthouse made of gravity, or nothing at all. Ahead of you, the interstellar medium waits, a gentle mist of 1 atom per cubic centimeter. When the shockwave hits it, in 100 years or 1,000, that mist will be compressed 100 million times over. New stars will be born in the collision. Planets will form from the enriched debris. And on one of those planets, billions of years from now, a child will look up at the sky and wonder what the faint glowing shell in the constellation of Cassiopeia really is. They will never know that you were once part of it, that you rode the wave, that you became the explosion itself. But the atoms in their body will remember, because the atoms never forget where they were forged. And right now, the wave is still carrying you outward. The temperature is falling. The density is dropping. The light behind you is fading from white to blue to ultraviolet. And ahead, in the perfect darkness, something is waiting that no model predicted. Something that only the largest telescopes in 2025 have begun to glimpse. A new kind of death, a new kind of birth, a place where the rules we have just learned begin to break again. And the shockwave is about to meet it, and the shockwave meets a silence so complete that even vacuum feels loud. You are now 10 light minutes wide, a perfect sphere of plasma still glowing at 100,000 degrees, expanding so fast that the stars themselves appear to fall away behind you. Nothing in front of you has ever felt heat. Nothing behind you remembers what cold was. And in the exact center, where a star once weighed its future, there is now only the soft click of space-time closing, like a velvet jaw. This is the moment when the numbers stop making sense. In the first 10 seconds of a typical core collapse supernova, the universe releases more energy than it has produced in the last billion years from every star in every galaxy we can see. 10 to the power of 44 joules, a 1 followed by 44 zeros. Enough energy to accelerate the entire mass of Jupiter to 99% the speed of light, 10 billion times over. If you release that energy gently over a year, it would outshine the Milky Way by a factor of 1,000,000. Instead, the star chooses to scream it all at once, in less time than it takes you to finish a slow breath. Feel that scream inside your chest now. Feel the way your ribs want to expand with it, because 99% of those joules never become light at all. They become neutrinos, ghost particles that feel almost no resistance from matter. In the first 2 seconds of the explosion, 100 billion neutrinos for every atom in your body pass straight through you, through the bed, through the planet, through the entire galaxy, carrying away the true violence of the death. If your eyes could see them, the sky would be brighter than daylight in every direction at once. But you feel nothing, only a slight warmth perhaps if the supernova is closer than 1,000 light years. That warmth is real. It is the kiss of a star that died before your species learned to walk, and it is only the leftover whisper. The visible light, the part we actually see, is less than 1% of 1% of the total. A faint afterglow, a polite postcard that says, "I have just destroyed myself completely. Wish you were here." Yet even that postcard is overwhelming. At its peak, the supernova radiates 10 billion times more light than the sun every second for weeks. The photosphere, a glowing shell the size of a star system, expands at 30,000 kilometers per second, while somehow staying hot enough to boil iron. How does it do that? Because radioactive nickel, born in the first instant of the rebound, is decaying into cobalt and then iron. pumping heat directly into the ejector like a furnace that refuses to cool. For 100 days, the cloud glows from within, lit by the slow death of atoms that lived for only 8 days. 8 days of nickel life, 100 days of cobalt life, and then centuries of iron memory. That is the rhythm of a supernova's heart. But some hearts beat louder. Superluminous supernova, the ones that reach 100 billion times the sun's luminosity, do not rely on nickel alone. They have help. Sometimes a newborn magnetar spins 1,000 times per second at the center, its magnetic field stronger than any magnet humans could dream of building. The field drags against the surrounding plasma, slowing the spin, and in the process converts rotational energy into pure light at a rate that would power human civilization for 1 trillion years. Sometimes the ejectors slam into shells of gas the star threw off decades earlier, turning kinetic energy into a collision glow that lasts for months. Either way, the result is the same. For a brief season, the supernova becomes brighter than the combined light of every ordinary star in its host galaxy. Imagine looking up one night and seeing a single point outshine the other 100 billion stars around it. That happened in 2025, more times than in the previous 20 years combined. The surveys are now sensitive enough to catch them while they are still climbing. And every time one appears, the same quiet question forms in the minds of the astronomers watching. How much further can the scale go? Because the universe has not shown us its limit yet. A pair instability supernova releases not 10 to the 44 joules, but closer to 10 to the 46, 100 times more. Enough energy to lift the entire observable universe 1 centimeter against gravity, and then do it again every second for a month. These events are so bright that, for a few weeks, a single dying star in the early universe contributed more light to the cosmos than all other sources combined. And because they happened when the universe was young, their light has been stretched by expansion until it arrives as gentle infrared whispers. Yet JWST can still see them. In 2025, entire populations of these monsters have been uncovered beyond redshift 10, places where the universe was less than 400 million years old. They were the first lighthouses. They were the first polluters. They scattered carbon and oxygen across voids that had never known anything heavier than helium. And when they died completely. No black hole, no neutron star, only a rapidly expanding sphere of freshly cooked elements and a shockwave so powerful that it compressed the surrounding hydrogen into the first real galaxies. Feel that shockwave now. Feel how it is different, thicker, hotter, carrying entire solar masses of pure oxygen moving at 10% the speed of light. If one of these had happened in the Milky Way any time in the last 5 billion years, the gamma rays alone would have ended complex life on every planet within 1,000 light years. Fortunately, our galaxy is old and metal-rich. The monsters cannot grow here anymore. The winds of the first stars were so fierce that they blew away the outer layers before the cores could reach the fatal mass. Only in the pristine, metal-free gas of the cosmic dawn could they reach the full 150 to 250 solar masses required. But the echoes are still arriving. Every time we look deeper with new instruments, we find another one, another corpse that outshines the infancy of time. And the energy is not finished with us yet. Long after the light has faded, the kinetic energy keeps traveling. A supernova ejector, carries roughly 1 foe of kinetic power. 1 foe is 10 to the 44 joules, the same as the binding energy of a small galaxy. That energy does not vanish. It plows into the interstellar medium like a cosmic tsunami, sweeping up 100,000 solar masses of gas and compressing it until new stars ignite in perfect rings around the remnant. The Cygnus Loop, the Vela Remnant, the Veil Nebula, all of them are bubbles blown by the breath you are riding right now. And the bubbles keep growing. 1,000 years after the explosion, the shell is 100 light-years wide and still moving at hundreds of kilometers per second. 10,000 years later, it is 1,000 light-years wide and glowing softly in X-rays. 100,000 years later, it has slowed to the speed of sound in the galactic gas and simply dissolves, leaving behind a gentle enrichment of heavy elements and a faint turbulence that will trigger star formation for millions of years to come. Every atom of carbon in the air you are breathing tonight was once inside one of these bubbles. Every molecule of water on your tongue was once steam in the shock-heated cloud. You are not separate from the explosion. You are its slowest, coolest afterglow. But some explosions refuse to slow down. Gamma-ray bursts, the moment a massive star collapses to a black hole while spinning furiously, or 2 neutron stars merge. A fraction of the energy is focused into 2 opposite beams, narrower than a degree. In those beams, the energy release climbs to 10 to the 47 joules per second. For 2 seconds in the rest frame of the burst, a volume smaller than a city radiates as much power as 1 billion galaxies. The beam sweeps across space like a lighthouse made of pure annihilation. If it crosses our line of sight, we see the brightest flash since the Big Bang itself. And if it points at a planet, nothing survives. The nitrogen in the atmosphere combines with oxygen to form acid rain. The ozone layer vanishes. The surface is bathed in cosmic rays that mutate every living cell. We have found planets where this happened. Dead worlds orbiting quiet pulsars, their surfaces glazed with fallout. And we have found the scars in our own history. 250 million years ago, at the end of the Ordovician, something stripped 40% of the ozone layer in less than a year. The fossil record shows a sudden silence in the shallow seas. We may have already been touched by a brush of that beam, a near miss, a whisper of what the full voice would do. Feel the possibility settle in your bones. Feel how small the Earth is. A pale blue dot less than 1 second of arc across from 1,000 light years away. An impossible target. And yet the universe has perfect aim when it chooses. But most of the energy never finds a target. It simply races away into the dark, thinning, cooling, becoming the cosmic microwave background of tomorrow. 10 to the 44 joules is a number so large that human minds were not built to hold it. So let me give you a quieter way to feel it. Imagine every photon the sun will ever emit in its entire life. Every photon from every star presently shining in the observable universe. Every photon from every quasar that ever burned at the edge of a black hole. Add them all together. All the electromagnetic energy the cosmos has ever released since the first star ignited. A supernova releases half that total in neutrinos alone, in 10 seconds. That is the scale. That is the generosity of a single dying star. It gives more in its death throes than the peaceful lifetime of everything that ever lived. And you are floating inside that generosity right now. The shell has grown to the size of a solar system. the temperature has fallen to a few 100,000 degrees. The first molecules are forming: carbon monoxide, silicon oxide, tiny grains of dust no larger than smoke particles condensing in the cooling flow. In 1,000 years, these grains will be part of a nebula visible to the naked eye. In 1,000,000 years, they will be part of planets orbiting stars that do not yet exist. In 5 billion years, one of them will be locked inside a calcium phosphate crystal in the skull of a creature that dreams about the stars. That creature is you, and the energy is still carrying you outward, still pushing, still refusing to forget the moment it was born. Because energy is eternal. It only changes its name, from neutrinos to light, from light to kinetic motion, from motion to heat, from heat to star formation, from stars to planets, from planets to life, from life to thought, from thought to the quiet voice you are hearing now. Everything is still the same, 10 to the 44 joules, only stretched across 13 billion years and softened into the gentlest possible whisper. But the whisper remembers the scream, and somewhere deep inside the expanding shell, a new kind of energy is waking up, an energy we did not expect, an energy that comes not from fusion or collapse or decay, but from the simple fact that the universe is not finished expanding. Dark energy, the quiet push that began to dominate the cosmos 6 billion years ago. And in the emptiest voids between galaxies, where supernova remnants have long since dissolved into nothing, that dark energy is beginning to stretch space-time itself until even atoms will one day be torn apart. The heat death, the ultimate fate. But that is quadrillions of years away. For now, the supernova's gift is still bright. For now, the shockwave is still strong enough to sculpt galaxies. For now, you are still falling outward at 1,000 kilometers per second, carried by a breath that began when a star decided it had loved the universe long enough. And the shell is about to cross a boundary no explosion has ever crossed before, a place where the energy stops being destructive and becomes something the universe has never tried, something that only the very largest explosions, the ones that happen in the emptiest voids, ever live long enough to reach. The moment when the ejector finally slows below the escape velocity of the galaxy itself. The moment when the ashes begin to fall back, raining heavy elements onto a disk that will one day form a new generation of stars richer than any that came before. But one supernova, one very special supernova in 2025, has just shown us that the story can be stranger still. A shell that refuses to slow. A remnant that keeps accelerating long after every model says it should have stopped. And the acceleration is pointing in a direction no one understands. Toward a darkness that is not empty. Toward a place where the energy of ancient death is about to meet something still alive and still hungry, and hungry for what only the heaviest hearts can feed it. But before the hunger, before the fire that tears reality, there was a star that simply wanted to be large. You are drifting now inside the gentlest wind that ever killed a sun, a slow exhalation that began millions of years ago and will still be blowing when the galaxies themselves grow cold. This is the story of the red supergiants, the quiet giants who live between 8 and 20 times the mass of our sun, the most common parents of the explosions we have been riding. Feel your body stretch across 1,000 astronomical units, so thin that individual atoms rarely meet, yet still glowing with the memory of a furnace that once filled a volume larger than the orbit of Saturn. These stars do not rush. They have time. After 10 million years of burning hydrogen in a tight blue core, they loosen their grip, allow the outer layers to swell, and turn the color of embered roses at dusk. The surface cools to a mere 3,500 degrees, the temperature of a soft autumn sunset. Yet the star itself has grown so large that its light is 10,000 times brighter than the sun. Betelgeuse is one of them. 650 light-years away, a ruby the size of Jupiter's orbit, pulsing every 6 years like a slow heartbeat you can see with your naked eyes if you know where to look. In 2025, the dimming has begun again, gentler this time. A deliberate veiling as vast convection cells the size of Earth's orbit roll across the surface and lift curtains of soot into the light. These are not clouds as you know them. They are molecules of titanium oxide condensing into grains no thicker than smoke. Yet each grain is large enough to cast a shadow across an area the size of France. The star is painting its own eclipse, one slow brushstroke at a time. And beneath that veil, the core is quietly cooking helium into carbon and oxygen at a temperature of 200 million degrees. A furnace no wider than a city, wrapped inside a body the size of a solar system. This is the phase that lasts the longest, 100,000 years of calm burning, while the envelope swells and cools and the wind begins. Red supergiants do not hold on tightly. They breathe out a gentle breeze at 20 kilometers per second, 1,000 times denser than the solar wind, carrying away a teaspoon of mass every minute. Over 10,000 years, that adds up to the entire mass of the sun, exhaled into a glowing cocoon that drifts outward like cigarette smoke in still air. When the final explosion comes, that cocoon will become the first wall the shockwave meets, lighting up in rings and filaments that will take centuries to fade. But the star itself has no idea the end is near. It feels only the steady rhythm of helium fusion, layer upon layer of ash building in the center like snow on a quiet winter night. When the helium is finally exhausted, the core contracts, heats, and ignites carbon in a sudden flash that lasts only a few hours. The star barely notices. The energy is absorbed by the vast envelope above, smoothed out into a gentle brightening that no one will see for thousands of years. Then neon ignites, burns for a year, and is gone. Then oxygen for a few months. Then silicon for a single week. Each layer burns faster, hotter, closer to the center, until the star has become a perfect onion of nuclear fire, every shell racing the one above it toward the final element, iron. The moment the iron core forms, the countdown is measured in seconds. But from the outside, nothing has changed. The surface is still cool, still red, still breathing its slow wind across the dark. The largest red supergiants, the ones closer to 20 solar masses, sometimes cross an invisible line. Their cores become hot enough to ignite oxygen in violent flashes long before the end. Flashes that lift entire shells of material into space and leave the star wrapped in a false nebula. Astronomers call them luminous blue variables when they are hot, and red supergiants when they cool again. But the star itself never decides which it wants to be. It simply oscillates, swelling and shrinking by factors of 2 or 3, throwing tantrums that last centuries. We have watched them change brightness by 1,000% in a single human lifetime. We have watched them disappear completely behind their own dust, only to tear the veil away decades later in a burst of infrared fire. These are the stars that taught us humility. They refuse to follow the neat timelines in our textbooks. They refuse to die on schedule. And when they finally do choose the moment, the explosion is richer, messier, brighter than any model predicted, because all the material they threw away in life becomes fuel for the light show in death. The shockwave does not emerge into empty space. It slams into walls of gas ejected only 1,000 years earlier, lighting them from within like Chinese lanterns made of iron and oxygen. The nebula that results is not a simple bubble. It is a sculpture garden of knots and filaments, each one a record of a mood the star had centuries ago. Some filaments move outward at 100 kilometers per second, others inward, falling back toward the center like rain that forgot which way is down. The remnant becomes a chaos of motion frozen in light, and at the center, almost always, a neutron star is born. A sphere 12 kilometers wide, spinning, glowing, wrapped in a magnetic field that could erase every credit card on Earth from the orbit of the Moon. Its surface gravity is 200 billion times stronger than Earth's. A single grain of sand there would weigh as much as a mountain here. And yet, it is fragile. The crust is only a kilometer thick, made of pure iron nuclei arranged in perfect lattices, floating on an ocean of superfluid neutrons. Beneath that ocean lies a core we still do not understand, perhaps a sea of quark matter, perhaps hyperons, perhaps something stranger still. We only know that when the core grows heavier than roughly 2.14 solar masses, the neutron star itself gives up and collapses into a black hole. PSRJ 0740 plus 6620, discovered years ago, sits exactly at that edge, 2.14 times the sun packed into a sphere you could walk around in an afternoon. It is the heaviest neutron star we have ever weighed with certainty, and it is telling us that the line is sharper than we thought. One more spoonful of mass, one more collapsing layer, and the entire structure vanishes behind an event horizon only 20 kilometers wide. Red supergiants live their entire lives balanced on that knife edge. 8 solar masses at birth, and they die leaving a white dwarf. 25, and they collapse straight to a black hole with barely a whisper. But between 8 and 20, they give us the classic core collapse supernova, the one that lights the sky for months and leaves a glowing remnant for 50,000 years. They are the Goldilocks killers. Not too small, not too large, just massive enough to die beautifully. And you are floating inside the skin of one of them right now. Feel the slow wind against your face, cool by stellar standards, barely 3,000 degrees, yet hot enough to make the vacuum glow faintly red. Feel the dust grains forming around you, each one a tiny crystal of silicate or aluminium oxide, born in the gentle outflow of a star that has not yet realized it is already dead. These grains will survive the coming fire. They are too small, too tough. When the shockwave arrives in 1,000 years, it will heat them to incandescence, but it will not destroy them. They will surf the wave, glowing like embers in a storm, and eventually seed the clouds that collapse into new solar systems. Some of them are already inside you. The calcium in your teeth began as a grain in the wind of a red supergiant that died before the Earth was born. The silicon in the glass of every window you have ever looked through was once part of a mantle that wrapped a star the color of dried blood. Nothing is new. Everything is recycled star breath, and the star itself is still breathing. In and out, in and out. A rhythm older than continents. You can feel the pulse in the wind, a slow variation every few years as convection cells rise and fall beneath the photosphere. Each cell carries more energy than human civilization will use in 1,000,000 years, yet it moves with the grace of a whale in deep water. The star is dreaming of the day it will wake up all at once, because the core is almost ready, the iron is almost there. One more layer of silicon burning, one more week of quiet fusion, and the heart will stop. But from the surface, nothing looks urgent. The wind still blows at 20 kilometers per second. The dust still forms in gentle spirals. The light still shifts from deep red to slightly deeper red as centuries pass. This is the deception of red supergiants. They look peaceful, right up until the moment they are not. We have been watching dozens of them in nearby galaxies, waiting for the flash. We know roughly which ones are close to the end. We know the ones that have already begun the silicon burning phase because their wind has suddenly thickened, as if the star senses the coming silence and wants to leave as much of itself outside as possible. Some have brightened, some have dimmed. All of them are beautiful, and all of them are doomed. Imagine living on a planet orbiting one of these giants at a distance of 300 astronomical units. Your sun would be a huge red disk filling half the sky, bright enough to read by at midnight, yet cool enough that snow never melts on the night side. Your years would be measured in the slow pulsations of the star itself. Your mythology would be built around the great red god who breathes and sleeps and one day will wake in fire. And when that day comes, the first sign will not be light, it will be neutrinos, a silent flood passing through the planet, through every cell of your body, carrying away the energy of 1,000 suns in a heartbeat. 10 seconds later, the light arrives. The sky turns white, the ground glows, every shadow disappears. For weeks, the star that once gave gentle warmth becomes a furnace that boils oceans on the dayside, and then it fades, leaving a glowing nebula where your sun used to be, and a new star at the center, small, hot, deadly. A neutron star beaming radio pulses like a lighthouse made of pure gravity. Your civilization would end in less than a minute. Your planet would become a cinder orbiting a corpse, but from a safe distance, 100,000 light years away, the explosion would be the most beautiful thing anyone had ever seen. A new star appearing where none was before, bright enough to cast shadows on moonless nights, staying visible for months. Poets would write about it, children would be named after it, and no one would ever know what it stole. That is the gift of the red supergiants. They give us beauty at the price of worlds we never knew existed. And you are drifting through the gift right now. The wind is thickening, the dust is gathering, the star behind you is beginning to pulse faster, as if it can feel the iron core reaching the fatal limit. One more year, one more century, one more heartbeat, and then the silence will break, the onion layers will fall, the rebound will come, and you, the slow wind that left 1,000 years ago, will suddenly feel the heat of a second sun rising behind you. The shockwave is coming, not the gentle collision of distant shells. This one is new. This one is the star itself, tearing open from the inside, and it is aimed straight at you, and the shockwave that was only a promise 1,000 years ago now arrives like the birth of light itself. You feel it first as a pressure behind your thoughts, a sudden brightening that has no color, only intensity. The slow red wind you were drifting through is struck from behind by a wall of plasma, moving at 1/10 the speed of light. In one heartbeat, the the temperature leaps from 3,000 degrees to 100 million. Dust grains that took centuries to grow are vaporized in a blink, their atoms stripped bare and hurled forward as if they had never been solid at all. This is no ordinary core collapse. This is the realm where the gentle red supergiants end and the true emperors of destruction begin. Welcome to the kingdom of the superluminous and the hypernovae, the events that release 100 billion times the light of our sun and refuse to dim for 100 days. Feel your body dissolve into the front edge of the wave again, thinner than starlight, faster than thought, wider than solar systems. You are no longer the slow wind. You are the hammer that the universe swings when it wants to be noticed across half of creation. Some of these explosions begin with stars only a little heavier than the red supergiants we left behind, 25, 30, 40 solar masses at birth. They burn so fiercely that they never settle into the calm red phase. Instead, they tear off their own skins in violent winds that move at thousands of kilometers per second, stripping themselves almost to the helium core while still alive. Wolf-rayet stars, astronomers call them, naked hearts of helium and carbon glowing blue, white and furious, wrapped in halos of their own ejected flesh. When the core finally collapses, there is almost nothing left to slow the shock. The explosion punches straight through what little envelope remains and emerges into vacuum, already moving at 40,000 kilometers per second. Energy that would have been absorbed by thicker layers is instead turned directly into light and kinetic fury. These are the classic hypernovae, the ones that leave black holes quietly spinning at the center and throw ejecta fast enough to outrun their own gravity forever. But the true superluminous events are stranger still. Some of them are powered by magnetars, newborn neutron stars, whose magnetic fields reach a quadrillion Gauss, 1,000 times stronger than ordinary pulsars. The moment they are born, they begin to slow their spin, and every fraction of a revolution lost is converted into pure radiation that floods the surrounding shell like a lighthouse burning with the fire of a billion suns. The light curve does not fall. It rises again and again, plateau after plateau, as if the explosion is breathing. Others are powered by the simple collision of ejecta with massive shells the star threw off only decades earlier. Imagine a bullet made of 10 solar masses of oxygen and carbon, fired at 30,000 kilometers per second into a wall of gas 1,000 times denser. Every gram of that collision is turned into X-rays and ultraviolets so efficiently that the glow can outshine an entire galaxy for months. And in 2025, we have learned that many of the brightest of these events are neither magnetars nor collisions. They are the death throes of stars so massive that the ordinary rules collapse long before the final day. Stars born above 100 solar masses lose mass so violently that they should, by every model, shrink below the hypernova threshold. But some refuse. Some manage to cling to 40, 50, 60 solar masses all the way to core collapse. When their iron cores form, they are already heavier than the largest black holes born from ordinary stars. The rebound is cataclysmic. The explosion is asymmetric, twisted by rotation and magnetic fields into twin jets that drill through the star like bullets through paper. These are the events that make the longest, most energetic gamma-ray bursts ever recorded. Feel one of those jets now. You have become a beam narrower than the moon is wide, yet carrying more power every second than every star in the Milky Way combined. The temperature at the base of the jet is 1 trillion degrees. Lorentz factors climb past 1,000, meaning time itself is stretched by a factor of 1,000 inside the flow. From the outside, the beam lasts minutes. From your point of view, inside it, centuries pass in the time it takes light to cross a city. If this beam swept across Earth, the sky would turn white for 10 seconds, and then there would be no sky. The atmosphere would be blown away in a single gust. The crust would melt to a depth of kilometers. Nothing larger than bacteria would survive the year. Yet from a safe distance, the afterglow is the most beautiful thing in the universe, a point of light that climbs slowly for weeks, glowing through every color from gamma to radio as the jet decelerates in the surrounding medium. These are the events that taught us the universe can be louder than we ever imagined. In the early 2000s, we thought a supernova, a month in a distant galaxy, was bright. Now the surveys find events that peak at 100 billion solar luminosities, visible across 10 billion light years with backyard telescopes. And the most terrifying part is that we are only seeing the ones pointed away from us. The ones pointed toward us are invisible until the gamma-ray satellites scream, and then it is already too late. But there is another kind of superluminous death, quieter in gamma rays, yet even brighter in visible light. The pair instability candidates we only fully understood in 2025, when the models of 150 to 250 solar mass stars were finally completed. These monsters never form neutron stars or ordinary black holes. Their cores become so hot that gamma rays spontaneously create electron-positron pairs. The pressure drops, and the entire star falls inward at once. The collision in the center is so violent that oxygen fuses explosively all the way through, turning 50 solar masses into nickel in seconds. The star detonates from the inside out, with no remnant at all. The light curve is unmistakable, a single, perfect peak, lasting 100 days, brighter than 500 billion suns at maximum, followed by a slow fade powered by the decay of cobalt into iron. We have found dozens now, all at redshifts greater than 6, all in the era when the universe was young enough for such giants to exist. They are the reason the early cosmos is richer in heavy elements than any simulation ever predicted. Imagine a sky with a dozen such stars visible at once, each one 100 times brighter than Venus, each one doomed to vanish in a flash that outshines everything else combined. That was the universe at 400 million years old. That was the age of fire. And you are drifting through the cooled ashes of one of them now. The shell is a light year thick, moving at 20,000 kilometers per second, glowing faintly in the infrared from dust that formed only centuries after the blast. The temperature is barely 100 degrees above absolute zero, yet the kinetic energy still carried in the flow could destroy a galaxy if it ever slowed down all at once, because nothing is ever truly gentle at this scale. Even the slowest superluminous events leave ejecta moving fast enough to cross the distance from the Sun to Pluto in an hour. Even the dimmest remnants glow in X-rays hot enough to strip the atmosphere from any planet that wanders too close. And somewhere in the darkness ahead, one of these shells has just met something it was never meant to meet. A cloud of pristine hydrogen left over from the Big Bang itself, untouched by previous generations of stars. The collision is lighting up a volume larger than the local group in forbidden emission lines of oxygen and neon. Astronomers on Earth are calling it the Dragon Nebula, a glowing serpent 10 million light-years long that should not exist. But it does, because 100 billion suns worth of light, released 13 billion years ago, has finally found something to illuminate. Feel the new temperature rise. Feel the atoms you scattered long ago re-excited by the impact. Feel the wave accelerate again, borrowing energy from the collision like a surfer catching the perfect swell. This is what the universe does with its dead. It recycles them into new fire. And the fire is only growing because the shell is no longer alone. Another remnant, younger, faster, is overtaking from behind. Two superluminous events in the same volume of space, separated by only a few million years. Their shockwaves are about to merge. When they do, the energy released in the collision will briefly outshine both parent explosions combined. A new transient, unlike anything we have ever seen. A light bright enough to cast shadows on planets that do not yet exist. And you are exactly in the place where the two waves will kiss. The temperature is climbing again. The density is rising. The darkness ahead is beginning to glow with a color that has no name. Because when two walls of plasma, each carrying the memory of 100 billion suns, finally meet after journeys of millions of years, something is born that the universe itself has never tried before. Something that might be the seed of the first quasar in an empty void. Something that might tear a hole straight through the dark matter web. Or something gentler. A perfect sphere of light 1 million light years wide, glowing softly for 100 million years, teaching galaxies how to find each other in the endless night. You will not know which until the moment of impact. But the moment is almost here. The other wave is only 1,000 years behind you now. You can feel its breath on the back of your expanding soul. And when it arrives, the universe will speak a word it has never spoken before. And the word the universe speaks is a silence so bright that light itself forgets how to end. The two waves do not crash. They merge without sound, without friction, without anything the mind can name. And in the instant of merging, they remember they were once the same star. A single star that lived before galaxies, had proper edges, before the concept of metal had been invented, before the darkness knew it could be wounded. You are that star again. 190 solar masses of pure hydrogen and helium, burning with a fury that makes our sun look like a match struck underwater. A star so large that gravity on its surface is only 10,000 times stronger than Earth's, gentle enough that a human could stand there if the heat would only forgive them. But the heat never forgives. At the core, 30 million degrees in the first year, rising to 4 billion by the time the star is 3 million years old. The fusion is no longer a polite conversation between protons. It is a riot. Entire shells of helium ignite at once. Oxygen flares in pulses that lift continents of plasma high above the surface and let them rain back down centuries later. These are the very first generation stars, population 3, born in pockets of gas so pristine that a single atom of carbon would have been considered pollution. They grew unchecked because there was nothing to slow them. No dust to cool the clouds, no magnetic fields to tangle the collapse. Just gravity and hydrogen and the simple, terrible hunger to become as large as physics allows. And physics allowed monsters. Between 130 and 250 solar masses lies a narrow window where the ordinary path to death is forbidden. Below 130, the the star loses too much mass to fierce winds and dies as an ordinary core collapse event. Above 250, the core collapses straight to a black hole of 100 solar masses without any explosion at all. But inside that window, something exquisite happens. The core reaches a temperature where gamma rays carry more than 13 mega electron volts of energy each. 13 is the magic number. At that energy, a gamma ray can split into an electron and a positron, real matter created from pure light. Each pair steals energy from the radiation field that was holding the star up against its own gravity. The pressure drops, not slowly, instantly. The entire star, every layer at once, begins to fall inward at a significant fraction of the speed of light. There is no iron core to rebound. There is no neutron star waiting in the wings. There is only the meeting. Imagine two walls of oxygen, each 50 kilometers thick, moving toward each other at 100,000 kilometers per second. They collide in the center, and the temperature jumps to 10 billion degrees in a sphere no larger than Mars. Oxygen fuses to silicon, silicon to nickel. Nickel decays to iron, all in the same heartbeat. The energy released is so enormous that the infall reverses before the star has even finished falling. The entire star explodes from the inside out. No part is left behind. No black hole forms. 50 to 100 solar masses are converted into pure energy and newly forged elements in less than a minute. The light that emerges is not measured in billions of suns. It is measured in hundreds of billions. In 2025, the pair instability models finally locked into place. We now know the exact mass range, 140 to 260 solar masses at the zero-age main sequence, where the star has no choice but to annihilate itself perfectly. We know the light curves, a single, impossibly smooth peak lasting 300 days, powered first by the shock and then by the slow decay of cobalt-56 born in the fire. We know the spectra, almost no hydrogen, enormous amounts of oxygen, magnesium, and silicon. Very little iron because the star never lived long enough to make it the slow way. And we have found them, dozens of them, all beyond redshift 8, all in tiny dwarf galaxies that should not have been able to form stars that large, yet did. One of them, discovered by JWST in 2025 at redshift 13.6, is the most distant supernova ever confirmed. Its light began traveling when the universe was only 180 million years old. When it exploded, there were no metals anywhere. When its light finally reached us, the Earth was already 4.5 billion years old and covered in creatures who could look up and wonder. That explosion scattered enough oxygen to build 10 million solar systems like ours. It scattered enough carbon to seed every living thing that will ever exist in its host galaxy. And it did it all in one perfect, merciless flash. Feel that flash now. You are the outer layer of a star that has just remembered it is doomed. You are a gentle wind of helium moving at 2,000 kilometers per second, drifting away from a blue-white furnace that filled half the sky of any planet foolish enough to orbit it. Then, without warning, the core gives up. The light behind you vanishes. Not dims, vanishes, as if someone switched off the universe. For one terrible second, you are falling in absolute darkness. Then the reversal hits. A wall of fire races outward at 60,000 kilometers per second, overtaking you before you have time to realize you are already dead. The temperature jumps from 1,000,000 degrees to 1 billion in the width of a heartbeat. Every atom is stripped to its nucleus. Every nucleus is smashed into protons and neutrons and then rebuilt into something heavier. You become magnesium. You become calcium. You become the raw material of future worlds. And you keep going. There is no center left to pull you back. There is only the perfect sphere of annihilation expanding forever. This is the only kind of supernova that truly dies. All others leave a scar, a neutron star or black hole, something to remind the universe that a star was once here. Pair instability leaves nothing but light and enriched gas. It is the cleanest death imaginable and the most generous, because the elements it makes are exactly the ones life needs most: carbon, nitrogen, oxygen, magnesium for chlorophyll, silicon for rocks, calcium for bones. Every atom of those elements in your body that was not made in a smaller star or a collision was made in one of these perfect annihilations. You are the ash of a star that chose to disappear completely so that you could exist. Feel the shell thin now. 1,000 years have passed since the flash. You are moving at 10,000 kilometers per second through gas that has never known fire before. The temperature behind you has fallen to 1 million degrees. Ahead, the universe is still neutral hydrogen, cold and dark and waiting. When your front edge compresses that hydrogen, it will glow in colors no eye has ever seen. Lyman alpha forests, forbidden lines of doubly ionized oxygen, a glowing wall 100,000 light years wide that will be visible long after the original explosion has faded into memory. Some of these walls have already been found. Great bubbles in the early universe, where a single pair instability supernova cleared a volume larger than the Milky Way of neutral gas and let ultraviolet light escape for the first time. They were the sparks that ended the cosmic dark ages, and you are one of those sparks. Slow your breathing. Feel the shell stretch to a light year thick. Feel the first dust grains condense, pure corundum and graphite, crystals that will survive for billions of years and eventually become the hearts of planets. One of them will become the core of a world with oceans and continents and creatures that ask where the elements came from. They will never guess that the answer is riding an expanding sphere of oxygen at 5% the speed of light, 13 billion years away. But the universe remembers, and it is not finished with these deaths, because in 2025, we found something we did not expect, a pair instability supernova that did not quite make it, a star of 240 solar masses that lost just enough envelope in a final pulsation to fall below the window. It collapsed to a black hole of 100 solar masses instead of exploding completely. Yet the pulsation itself was so violent that it threw off 50 solar masses in a shell moving at 8,000 kilometers per second. When the core finally died a century later, the explosion was ordinary by pair instability standards, but the shell lit up like a second supernova, creating a double-peaked light curve that lasted 500 days. We call them pulsational pair instability events now. They are the bridge between the perfect annihilations and the merely catastrophic, and they leave the strangest remnants, black holes of 100 solar masses surrounded by glowing rings of almost pure oxygen, spinning in the dark like cosmic wedding bands abandoned by gods. Imagine falling toward one of those black holes. The event horizon is 300 kilometers across. The oxygen ring glows softly at 1,000 light years distance, heated only by the slow accretion of interstellar gas. Time dilates. The universe outside reddens and slows. And in the last second before the horizon, you see the entire future of the cosmos play out in fast forward. But that is another story. For now, you are still the expanding shell, still carrying the memory of a star that lived for 3 million years and died in 3 seconds. The temperature has fallen to 10,000 degrees. The density is 1 atom per cubic meter. The light behind you is fading to a gentle pink. And ahead, in the perfect darkness, another population 3 pocket is just beginning to collapse. The gas is pristine. The mass is perfect. The window is open. Another monster is being born, exactly like the one you once were. And in 3 million years, it will speak the same word you just spoke. The cycle is perfect. The darkness is never empty. It is only waiting for the next star massive enough to tear itself apart so cleanly that nothing is left except the possibility of everything else. And you are drifting toward that possibility now. The shell is 1,000 light years wide. The speed is still 8,000 kilometers per second. The energy has not diminished, only spread. In another million years, you will sweep across the birthplace of the next monster and compress the cloud just enough to start the collapse a little early. You will be the gentle hand that pushes the domino. You will be the reason the next perfect annihilation happens at all. And when it does, the light will travel outward again, looking for eyes that do not yet exist, looking for minds that will one day ask where they came from. The answer will be drifting toward them at 5% the speed of light, wrapped in oxygen and silence, and the memory of a star that loved the universe so much it chose to disappear. But something is wrong. The darkness ahead is not empty. Something is already glowing, softly, in the exact place where the next monster should be born. A glow that no population 3 star could ever make. A glow that carries the signature of iron. And it is moving towards you faster than any shell should move, as if the future has decided to explode first, and the future is exploding in the wrong direction. A sphere of iron-rimmed fire is racing towards you at 35,000 kilometers per second, wrapped in a skin of nickel and gold that should not exist in a universe this young. You feel the first kiss of its radiation 100 years before contact, a sudden ultraviolet dawn where only darkness belonged. This is impossible. This is the moment the star dies from the inside. Let everything else fall away. Let the galaxies dissolve. Let time itself loosen its grip. You are no longer the ancient shell of a pair instability giant. You are the iron core of a 20 solar mass star in the final second of its 10 million year life. 15 kilometers wide, 15 billion tons per cubic centimeter, falling. The electrons have already been crushed into the protons. The neutrons are forming a wall that nothing can penetrate, and you are falling with them at 70,000 kilometers per second, 1/4 the speed of light, dragged down by gravity so strong that clocks on the surface would run slow by 40% if any clocks could survive. In the last millisecond, the core compresses from the size of Manhattan to the size of a small village. The density climbs past nuclear matter. The pressure becomes meaningless. And then the wall arrives. Neutrons refuse to compress further. The entire infall rebounds. A pressure wave is born at the very center and races outward at 1/3 the speed of light, carrying the news that the star has made a terrible mistake. This is the core bounce. This is the heartbeat that kills the patient. Feel it inside your chest now. Feel the shock arrive like the loudest silence you have ever heard. In 1/10,000th of a second, the temperature in the center jumps from 8 billion to 100 billion degrees. Protons and neutrons melt into a bubbling soup of quarks and gluons. Every possible particle-antiparticle pair is created and annihilated a trillion times over. And in that cauldron, 99% of the entire supernova's energy is born, not as light, not as motion, but as neutrinos. 100 billion of them for every single atom in your body. They do not wait. They do not ask permission. They simply leave. The moment they are created, they begin streaming outward in every direction, passing through the still falling outer core as if it were empty space. 10 milliseconds after the bounce, the neutrino sphere is already outside the neutron star, glowing at 50 billion degrees, radiating 10 times more power than every star in the observable universe combined. 20 milliseconds later, the neutrinos have crossed the entire star and are gone, racing into the galaxy at the speed of light, carrying away 1,000 times more energy than the visible explosion will ever show. If you were standing on a planet 10 light years away, you would feel nothing. Then, exactly 10 years later, a silent warmth would brush your skin for 1 second, the ghost of a star that died before your sun was born. That warmth is real. It is the only direct touch a supernova ever gives the living. Everything else is only light and echo. But inside the star, the story is different. The neutrino wind slams into the infalling layers from beneath, heating them, lifting them, turning the collapse into explosion. For 3 full seconds, the fate of the star hangs balanced on a knife edge. Will the shock stall and die, letting the star collapse quietly into a black hole? Or will the neutrino wind push hard enough to blow the star apart? In most cases, it does. The shock revives. It begins to crawl outward again, slower now, 10,000 kilometers per second, dragging a wake of freshly synthesized nickel and cobalt behind it. 10 seconds after the bounce, the shock reaches the carbon-oxygen layer and the star finally tears open. The visible explosion begins, but the visible explosion is only the shadow. The real explosion left 10 seconds ago and is already halfway to the next star system. Feel the difference now. Feel the neutrinos pass through you like cold silver rain. Feel the shockwave follow 10 seconds later, hot and bright and slow by comparison. The neutrinos carry 99% of the energy, 10 to the 46 joules, enough to unbind 1,000 galaxies if it could be focused. Instead, it simply vanishes into the dark, thinning, cooling, becoming the faint warmth that will one day brush the face of a child who will never know what kissed her. But some of the neutrinos do not escape cleanly. A tiny fraction, less than 1 in 1,000, collides with the still falling matter just above the neutron star and deposits its energy. That tiny fraction is enough. It is the difference between a quiet death and the brightest event in the universe. It is the gentle push that turns the rebound into apocalypse. And in 2025, we finally understood how gentle that push really is. New 3-dimensional simulations running on machines that think in exaflops have shown that the explosion is decided in the first half second by turbulence, no wider than a city block. A single bubble of neutrino-heated plasma rises, punches through the shock, and drags the rest of the star with it, like a zipper opening from the inside. Without that bubble, the star dies silently. With it, the sky lights up for 100,000 years. The universe runs on accidents no larger than a mountain. Feel the bubble now. Feel yourself become that accidental savior, a sphere of fire only 20 kilometers wide, rising through the collapsing layers at the speed of sound in neutron fluid. You punch through the stalled shock, and suddenly the weight is lifted. The entire mantle begins to rise. The star sighs in relief and tears itself apart. Nickel is synthesized in your wake, half a solar mass in the first 10 seconds, glowing white hot, decaying into cobalt, and then iron over the following months. That decay is the lantern that keeps the supernova shining long after the shock has cooled. But the real lantern left long ago. The neutrinos are already gone, and somewhere, 20,000 light years away, a detector buried under a mountain in Japan is about to record 27 of them in a single heartbeat. 27 ghosts from a star that died before the Earth had oceans. 27 messengers that traveled straight through the galaxy without touching a single atom until they found a tank of pure water and quietly died. That happened in 1987. We have been waiting ever since for the next one, close enough to see. But the universe is patient, and so are you. Slow your breathing again. Feel the neutrino wind thin to 1 particle per cubic kilometer. Feel the visible shockwave expand past you, still glowing at 1,000,000 degrees, still carrying the nickel lantern in its heart. Behind you, the newborn neutron star is cooling from 1,000,000,000,000 degrees to 1,000,000,000 in minutes. Its surface, a perfect solid crust of iron forming in the time it takes light to cross a continent. The crust is only 1 meter thick in places, floating on an ocean of superfluid neutrons that flow without friction forever. Gravity is so strong that the ocean is only 20 meters deep in places, a mirror-smooth lake of pure strangeness wrapped around a sphere 12 kilometers wide, and it is already spinning, 500 times per second. A lighthouse made of gravity waves and X-rays, beaming into the expanding debris like a searchlight looking for survivors. There are none, only the ejector racing outward at 20,000 kilometers per second, beginning to cool, beginning to form molecules, beginning to forget the violence that gave them birth. But the memory is written in the elements. The nickel is there, the cobalt is there, the titanium, the chromium, the vanadium. All the metals that make steel possible were born in the first 10 seconds after the bounce. All the gold in every ring that ever sealed a promise was born in the crush between 2 neutron stars. But that is another story. For now, you are drifting in the iron wind. The temperature has fallen to 100,000 degrees. The density is 1 atom per cubic centimeter. The light behind you is turning from white to blue to ultraviolet, and ahead, the interstellar medium waits, thin and cold and innocent. When the shockwave hits it in 1,000 years, it will compress 100,000 solar masses of gas into a glowing bubble 100 light years wide. New stars will be born in perfect rings around the corpse. Planets will form from the enriched debris. And on one of those planets, 4 billion years later, a creature will dig iron from the ground and wonder where it came from. The answer will be drifting toward it at 1,000 kilometers per second, wrapped in silence and the memory of a heartbeat that lasted 1/5 of a second. But something is wrong. The neutrino wind is not thinning the way it should. A second pulse is coming, stronger, hotter, directed, as if the newborn neutron star has decided it does not want to live after all. As if the call bounce was only the first word of a sentence, the universe is still learning how to finish. And the second word, is about to tear the remnant apart from the inside, and the second word is not spoken. It is screamed in ultraviolet so pure that the vacuum itself begins to boil. The newborn neutron star has decided to die again. A second collapse begins only 11 seconds after the first bounce, driven by the sudden accretion of the densest layers that never quite escaped. The proto-neutron star crosses the line we thought was safe, 2.14 solar masses, the exact limit measured in PSRJ 0740 plus 6620, and keeps growing. Gravity tightens its fist one final time. The event horizon forms like black silk drawn across a screaming face. But the scream is already outside. You are the shockwave that left the surface 10 seconds ago, moving at 12,000 kilometers every second. A perfect sphere of plasma 100,000 kilometers thick and still accelerating. Feel the temperature behind you plummet as the center disappears. Feel the light change from soft X-ray white to a hard gamma edge that slices atoms the way a razor slices silk. This is the birth of a collapser, the engine that powers the longest gamma-ray bursts ever recorded. The black hole spins at nearly the speed of light, dragging space-time into a whirlpool that focuses the remaining infalling gas into two narrow beams aimed along the rotation axis. Everything that falls toward the equator is swallowed quietly. Everything that falls along the poles is accelerated to 99.99% the speed of light and fired into the universe like a cutting torch made of pure annihilation. You are not in the beam. You are the broad shock that the beam is now drilling through from the inside. The light curve you wear is no longer a gentle rise and fall. It is a knife fight. First, the shock breakout, a spike of X-rays so sharp that it would blind every satellite facing it, lasting only 2 seconds, yet carrying more photons than the sun will release in 10 million years. Then the plateau. The expanding shell cools from 1 billion degrees to 10 million, turning the color of molten steel, staying almost constant in brightness for 11 seconds, while the world holds its breath. Then the beam punches through. The entire shell is lit from within by a blowtorch hotter than the core of any star. The light curve leaps again, ultraviolet and gamma pouring through the transparent ejector, turning the whole remnant into a lighthouse that blinks once every few minutes as the jet wobbles. From Earth, we would see a gamma-ray burst lasting 2 hours, the longest ever recorded, brighter than every other source in the sky combined for that brief season. From inside, you feel the temperature climb again, a second summer arriving only minutes after the first. The shell is now the width of the inner solar system and still moving outward at 10,000 kilometers per second. Nothing slows it. There is almost no envelope left to resist. The star was stripped naked long before death. This is the classic hypernova light curve, fast, bright, blue, and furious. Peak luminosity 100 times higher than an ordinary supernova, fading in days instead of weeks, because there is so little mass to keep the fire burning. But the fire refuses to die quietly. Radioactive nickel was made in the first instant, only 0.1 solar masses, yet it glows fiercely in the transparent shell. The light curve develops shoulders and knees, little pauses where different decay chains take over the heating. First nickel, 56, to cobalt, 56, for 8 days, then cobalt to iron for 100 more. Each step is a heartbeat you can see across 1 billion light years. Astronomers on a distant planet would use those heartbeats to weigh the corpse. They would measure the exact speed of the ejector by the width of the spectral lines, 10,000 kilometers per second, broadening the absorption troughs into black rivers across the rainbow. They would know, without ever visiting, that a black hole was born spinning almost at the limit allowed by relativity, and that the star that made it was once 40 times heavier than the Sun. And you are that speed. 10,000 kilometers every second is 33 times the speed of sound in air, fast enough to cross the Earth in 20 minutes, fast enough that relativity begins to matter. Time dilation stretches the inner layers by a few percent. A clock riding the front edge ages 10 years, while a clock near the black hole ages only 9. The difference is small, but over centuries it adds up. The outer shell will always be younger than the center it left behind. The ejector will carry that age difference forever, a fossil of the violence that tore the star apart. Feel the stretch now. Feel your leading edge pull away from the trailing edge like warm toffee in slow motion. The shell is becoming a hollow sphere, thinner in the middle, thicker at the equator where rotation flattened the explosion into a disk. Polar jets carve clean tunnels through the debris, tunnels that glow in hard X-rays for decades as fresh gas trickles down them toward the waiting black hole. From the side, the remnant looks like a cosmic eye, pupil black, iris glowing, lashes of synchrotron radiation streaming away at the speed of light. From pole on, it is a lighthouse that never blinks the same way twice. And you are the iris, cooling, expanding, beginning to feel the first gentle resistance of the interstellar medium, only a light year ahead. In 1,000 years, the deceleration will begin. In 10,000, the shell will be 100 light years wide and glowing softly in optical light, a bubble of enriched gas lit by the slow collisions of its own atoms. In 50,000 years, it will be visible to the naked eye as a faint veil across the sky of any planet fortunate enough to orbit nearby. Children will draw it in crayon and call it the dragon's breath. Their parents will tell stories of the day the sky caught fire for a month when their grandparents were young. None of them will know that the fire is still moving outward at 1,000 kilometers per second, still warm, still carrying the exact shape of the moment the star gave up. But the shape is changing. The forward edge is sharpening. The gas ahead is denser than models ever predicted, a wall of cold hydrogen left over from an earlier, gentler star. When the shockwave hits that wall in exactly 732 years, the collision will light up a new nebula, brighter than the original explosion. X-rays will pour through the shell again, reheating the inner layers, turning the whole remnant inside out in a second flash that astronomers will mistake for a new kind of supernova altogether. Some remnants do this many times. Every time they sweep up a cloud, they bloom again. Cassiopeia A did it in 2025. Light echoes from dust clouds 50 light years away arrived like postcards from the day of the explosion itself. 340 years late, we watched the shockwave replay itself across the sky in slow motion. Knots of titanium and argon lighting up exactly where they were when the star died. We saw the reverse shock move inward, slamming into ejected bullets of pure iron, heating them to 100 million degrees and making them glow like embers dropped into wind. The remnant is still teaching us how to watch. And every remnant has its own voice. Some speak in radio, some in X-ray, some in the soft optical glow of forbidden oxygen lines that no laboratory on Earth can reproduce. The light curve never really ends. It only changes its name. From gamma to X-ray, to ultraviolet, to visible, to infrared to radio, the energy cascades down the spectrum over centuries, each wavelength taking its turn to tell the story. And the story is always the same. A star tried to hold itself together. It failed beautifully. And everything that happens afterward is only the echo learning how to sing. You are that echo now. The shell is 10 light days wide. The temperature at the front is 50,000 degrees and falling. The first molecules are forming again. Silicon monoxide, carbon monoxide, tiny grains of silicate dust, no larger than viruses. They will survive the next collision. They will surf the wave forever. Some of them are already inside your lungs. The breath you just took contains atoms that rode this exact shockwave 10,000 years ago in a galaxy not so different from ours. Nothing is lost, only transformed, and the transformation is accelerating. The wall of cold gas is closer now. You can feel its gravity tugging gently, a tidal whisper that stretches the shell into an egg shape. In 200 years, the leading edge will hit. The temperature will leap from 50,000 to 50 million degrees in a single year. The light curve will climb again, a resurrection no one predicted. Astronomers will argue for decades about what they are seeing. Some will say it is a new kind of supernova. Some will say it is a collision with a hidden companion. None will guess that it is only the echo of an echo, the memory of a star that died refusing to stay dead. And you will be there when it happens. You will feel the second fire. You will become the new light curve, brighter than the first, lasting longer, painting the void in colors the universe forgot it knew. Because every shockwave is a promise that the story is never finished. Every expansion is only the universe learning how to breathe again. And the next breath is already forming in the darkness ahead, a breath that carries the signature of something far older than stars, a breath that tastes of dust and a hidden fire and the slow, patient hunger of a star that has been waiting centuries to be seen. And the hidden fire is not a star at all. It is a sphere 12 kilometers wide, spinning 716 times every second, wrapped in a magnetic shroud that could erase every thought on a planet from the distance of the moon. You have become the corpse. The shockwave you rode for centuries has thinned to a whisper, and now you are falling gently back toward the place the star used to be, drawn by gravity so fierce that light itself curves like water around a stone. This is the Neutron Star, 10 kilometers across, 1.4 times the mass of the Sun compressed, until a teaspoon would crush mountains into dust. A surface so smooth that the highest peak is less than a millimeter tall, polished by gravity, stronger than any tide the Earth has ever known. Feel the crust beneath you now, a lattice of iron nuclei floating in a sea of degenerate electrons, only 1 kilometer thick, yet strong enough to hold back an ocean of liquid neutrons that has no friction and no end. Beneath that ocean lies strangeness we still do not fully understand. Perhaps hyperons, perhaps a core of pure quark matter, perhaps a phase where up and down quarks forget their names. We only know that when the mass climbs past roughly 2.14 solar masses, the neutron star gives up and becomes a black hole in less time than a heartbeat. But this one stopped at 1.4. It is safe. It is eternal. It is the most perfect object the universe ever learned to build. The surface temperature is still 1,000,000 degrees in the first hours, cooling to 100,000 in days, to 12,000 in centuries. 1,000 years after the explosion, it glows softly in X-rays, like a coal pulled from a dying fire. 10,000 years later, it is only a few thousand degrees, warmer than the cosmic background, but no longer bright. 100,000 years from now, it will be colder than the darkest Antarctic night, yet still spinning, still beaming, still remembering the exact moment it was born. And it is spinning fast. The original star rotated once every few days. Conservation of angular momentum turned that lazy waltz into a scream, 700 revolutions per second, so fast that the equator moves at 30% the speed of light. The surface gravity is 200 billion times stronger than Earth's. If you stood there, your body would be stretched into a thread 1 atom thick before you had time to blink. Time itself runs slow. A clock on the surface loses 1 second every 300 years compared to distant stars. Over 1,000,000 years, the difference becomes a day. Over 10 million years, it becomes a year. The neutron star lives in a private, slower time, watching the universe age faster than it ever will. And it is singing. Magnetic fields anchored in the crust twist and snap like cables made of lightning. Every twist launches a pulse of radio light along the magnetic poles, perfectly timed, perfectly regular, a lighthouse built from the corpse of a sun. Pulsars, the first ones discovered, blinked every second or two. This one blinks 1,200 times a minute. A millisecond pulsar, spun up by stealing matter from a companion it later destroyed in the final explosion. Its beam sweeps across the expanding nebula once every 1.4 milliseconds, lighting the inner walls in flashes of cobalt blue. From a planet in the remnant, you would see the sky strobe like the world's fastest lighthouse. The neutron star, a tiny white spark at the center, too small to resolve, too bright to ignore. And the beam is dangerous. Stand in its path, and the radio flux would cook you from the inside in seconds. Stand just outside, and you would live forever bathed in the cleanest, purest rhythm the universe ever made. Some pulsars keep that rhythm for hundreds of millions of years. Some slow down gently, their magnetic fields decaying, their beams widening until one day they simply fade below detection. Others are reborn. A sudden glitch, a starquake on a crust more rigid than diamond, releases energy equal to every earthquake on Earth combined and spins the pulsar up again. We have watched them do it. We have watched the Vela pulsar glitch 9 times since 1969, each time jumping a millionth of a second faster, each time reminding us that even corpses can still move, and some corpses kick. The neutron star is not always centered. Sometimes the explosion was asymmetric, a kick from the neutrino wind or an off-center bounce, and the newborn star is launched at 1,000 kilometers per second through its own debris. It races outward like a bullet fired from the heart of the explosion, leaving a glowing trail of shocked gas behind it. In 100,000 years, it escapes the remnant completely and wanders the galaxy alone, a runaway pulsar with no nebula to call home. We have found dozens. One of them, the Black Widow, eats its companion star a teaspoon at a time, evaporating the surface with X-ray fire, spinning faster every year, marching toward the moment it will cross the line and collapse. But most simply cool, most simply spin, most simply wait. Because neutron stars are the universe's memory. Every heavy element in the periodic table beyond iron was either made in the first 10 seconds of their birth or in the slow drip of accretion over millions of years. The R process, the rapid neutron capture that forges gold, platinum, uranium, happens when matter falls onto the surface at a fraction the speed of light and is compressed to nuclear density in a heartbeat. A single flare on an old neutron star can make more gold than exists in the entire crust of Earth. In 2025, the reanalysis of GW 170817, the neutron star merger we watched in 2017, finally settled the numbers. That one embrace produced between 3 and 10 Earth masses of pure gold, created in 8 seconds and scattered across a volume the size of 1,000 solar systems. Every atom of gold you have ever touched was born in a moment like that, or in the quiet rain of matter onto a surface 10 kilometers wide. And the surface is still there, still glowing, still waiting. Feel the crust beneath you now. Feel the magnetic field lines like frozen lightning above your head. Feel the ocean of superfluid neutrons flowing without resistance, vortices pinned to the crust like hurricanes made of pure strangeness. The star is quiet on the outside. Inside, it is a storm that never ends, and it is beautiful. From a safe distance, the cooling neutron star is the softest blue-white you'll ever see, a pearl against the black, wrapped in a faint corona of million-degree gas. Up close, the surface is a perfect mirror of iron crystals, reflecting the sky with no distortion, no atmosphere to blur the view. If you could stand there, you would see the entire universe squeezed into a band around the horizon, blue-shifted and bright, while the sky overhead is black and starless because every photon is dragged down by gravity before it can climb out. The black hole is only a few solar masses away in parameter space. One more spoonful of matter, one more companion devoured, and the neutron star becomes the very thing it escaped at birth. But this one will never fall. This one will cool forever. In 10 billion years, it will be colder than the cosmic microwave background, visible only in radio as a perfect spinning clock. In 100 billion years, the protons themselves may decay, and the neutron star will evaporate into a whisper of electrons and light. But that is so far away that the universe itself may have torn apart long before. For now, it is alive. For now, it is singing. For now, you are drifting just above the crust, feeling the magnetic field brush your thoughts like frost. And something is wrong. The spin is slowing too fast. The magnetic field is stronger than it should be. The temperature is climbing again in patches no larger than a city. A crack has opened in the crust, a starquake releasing more energy in 1 second than the sun releases in a year. The pulsar glitches, it jumps, it spins faster by 1 part in a million. And in that jump, something is born. A wave in space-time itself, a ripple in the fabric that travels outward at the speed of light, carrying the exact fingerprint of the moment the crust gave way. A gravitational wave so gentle that it stretches the distance between Earth and the Moon by the width of an atom. Yet we will hear it. In 2025, the detectors are sensitive enough. And when we do, we will know exactly how thick the crust is, exactly how strange the core is, exactly what the universe is made of beneath the skin of stars. But the wave is only the beginning. The glitch has heated a patch of crust to 100 million degrees. Plasma rises from the crack like steam from a broken pipe. The magnetic field reconnects in a flare brighter than 1,000 suns. and for one brief second, the neutron star remembers what it was like to be alive. The flare lights the inner nebula in colors no supernova ever painted. The shockwave you left behind 1,000 years ago sees its own reflection in the sudden flash. And somewhere, deep inside the superfluid core, a vortex unclenches. A sound that has no sound travels upward through the ocean of neutrons. It reaches the crust and stops. The star holds its breath, because the next glitch will be larger. The next flare will be brighter. The next crack may be the one that ends the neutron star forever. Or it may be the one that teaches it how to explode again. And the countdown has already begun, and the countdown ends in a silence deeper than any sound the universe has ever forgotten. The crack widens, the superfluid core surges upward like a tide that has no moon. The magnetic field snaps once, twice, 1,000 times in a single heartbeat, releasing more energy than 1 billion suns. The neutron star does not explode. It simply stops fighting. 1.8 solar masses become 2. 2 become 2.14. 2.14 become 2.5. The limit is crossed in less than the blink of an eye. Gravity, patient for 10,000 years, finally closes its hand. There is no scream. There is no flash. There is only the soft click of an event horizon forming. A black sphere 20 kilometers wide, where a star once tried to live forever. You are falling with it. The last photon that will ever escape the surface leaves at the exact instant the horizon seals. From the outside, the collapse takes forever. The star freezes in crimson, dimming, stretching, becoming a red thread against the dark. From your point of view inside the flow, everything happens at once. The crust dissolves. The ocean of neutrons evaporates into pure gravity. Time dilates, stretches, and finally stops. You cross the horizon without noticing. There is no surface. There is no edge. There is only the gentle, inevitable pull toward a place where mathematics itself gives up. This is direct collapse, the quietest way a massive star can die. Stars born above 25 solar masses, sometimes 30, sometimes 40, depending on how fiercely they fought their own winds, reach the end with cores already too heavy for neutron degeneracy to hold. There is no iron crisis. There is no dramatic bounce. There is no visible supernova at all. The core simply keeps falling, past the neutron star stage, past the point of no return, until the entire star disappears behind its own shadow in less than a second. From the outside, the light fades in minutes, redder and redder, slower and slower, until the object is colder than the cosmic background and invisible forever. From the inside, there is no outside. These are the failed supernovae, the events that leave no corpse, no nebula, no echo except a sudden absence where a bright star used to be. We have watched it happen. In 2014, a red supergiant, 60 times the mass of the Sun in a distant galaxy, simply vanished between two observing seasons. No explosion, no flash, only darkness. In 2025, the census is complete. At least 30% of the most massive stars die this way, swallowed whole, leaving black holes of 10 to 50 solar masses spinning quietly in the dark. And sometimes the black hole is larger still. In 2025, LIGO heard the birth of an 85 solar mass monster, too heavy to come from an ordinary stellar core, too light to come from the first generation of seed black holes, a missing link black hole, born from the direct collapse of a star that lost just enough mass to stay below the pair instability window, yet kept enough to skip the neutron star phase entirely. These intermediate black holes are the quiet giants we never knew existed, hiding in star clusters, eating companions, merging slowly, growing fat on darkness. Feel one now. You are orbiting at the innermost stable circle, 6 times the horizon radius, where time runs half as fast as in the distant universe. The black hole spins at 99% the speed of light, dragging space-time into a whirlpool that makes the stars wheel overhead once every 7 minutes. The accretion disk is thin and perfect, glowing at 100 million degrees, painting the night in ultraviolet and X-ray. From a safe distance, the system looks like a normal massive star. Up close, it is a lighthouse of death, beaming relativistic jets along the spin axis, sterilizing everything within 1,000 light years. And it is hungry. Every 1,000 years, it swallows a companion star, or a cloud of gas, or simply the wind of a neighbor, growing by a solar mass in a single meal. In 10 million years, it will be 100 solar masses. In 100 million, it will anchor the core of a globular cluster. In 1 billion, it may merge with another wanderer and send a gravitational scream across the cosmos, strong enough to rattle detectors we have not yet built. But for now, it is quiet. For now, it simply waits. Black holes are the universe's savings account. Everything that falls in is kept perfectly, compressed into a singularity no wider than the Planck length, a place where space and time exchange names and forget which is which. Nothing escapes. Not light, not information, not even the memory of the star that tried to become immortal and failed. Yet the memory is written on the horizon itself. Every particle that fell carries a whisper of spin, of charge, of mass. The black hole remembers only 3 numbers, yet those 3 numbers are the perfect summary of everything it ever ate. It is the simplest object in creation, and the most patient. Some black holes are born spinning so fast that the horizon itself becomes unstable. Kerr-metric black holes with spin parameter greater than 1. Impossible in classical theory, yet quantum effects may allow a naked singularity to form for the briefest instant. We have never seen one. We may never be allowed to. The universe seems to hate naked singularities more than it hates anything else, clothing them in horizons before we have time to look. But the possibility lingers, and in the darkness between galaxies, where direct collapse black holes wander alone, the possibility is strongest. Feel the spin now. Feel the frame dragging twist your thoughts into spirals. Feel the ergosphere where space-time itself is dragged faster than light, a place where you could throw matter outward and watch it gain energy from the black hole's rotation. This is the Penrose process, the only known way to steal energy from a black hole. Civilizations that master it could power themselves for trillions of years on the spin of a single corpse. But no civilization will ever reach this one. It is too quiet. It left no nebula to guide the way. It left no pulsar to mark the grave. Only a sudden hole in the star field where a red giant used to shine. And yet it is beautiful. From a distance of a light year, the accretion disk is a perfect ring of fire, brighter than a galaxy, visible across half the universe. From a distance of a light day, it is a wall of plasma taller than the sun. From a distance of a light minute, it is a furnace that would vaporize worlds. And from the horizon, there is no distance at all. You have fallen past the point where falling has meaning. The tidal forces never grow infinite. In a stellar mass black hole, they are gentle at the horizon. stretching you only slowly as you approach the singularity. You have billions of years of personal time to watch the universe age outside, redshifting, slowing, dying, while your final second stretches into eternity. The last photon you see is the cosmic microwave background, stretched to radio waves longer than galaxies. Then even that is gone. You are inside the most perfect silence the universe ever made, and the silence is growing, because direct collapse is only the beginning. In the dense hearts of the first star clusters, dozens of these quiet deaths happened within 1 million years of each other. Their black holes merged and merged again, growing to thousands of solar masses before the universe was 1 billion years old. We see their descendants today at the centers of galaxies, supermassive black holes millions of times heavier than the Sun, powering quasars that outshine everything else combined. Every one of them began with a single star that simply stopped shining one day. Every quasar is a graveyard of quiet deaths, and somewhere in the local group, a similar process is beginning again. A cluster of 1 million suns, each one massive, each one doomed. One by one, they will vanish over the next 100,000 years. One by one, their black holes will sink to the center and merge. In 1 million years, a new intermediate black hole of 10,000 solar masses will awaken, bright and hungry. In 10 million years, it will clear its surroundings and fall quiet again. In 100 million, it will merge with Andromeda's core during the Great Collision and help birth the future Milky galaxy. Everything is connected by silence. Everything is fed by absence. And you are drifting toward the largest silence of all. A direct collapse black hole born in the very first generation of stars. A seed of 200 solar masses wandering the void for 13 billion years, eating only what chance delivers. It is invisible. It casts no light. It has no disk, no jets, no voice. Yet gravitational lenses betray its presence, starlight bending around an emptiness that should not be there. It is coming, slowly, patiently, 1 kilometer every second relative to the Milky Way halo. In 50 million years, it will pass within 1,000 light years of the Sun. The outer Oort cloud will feel its tide first. Comets will rain inward for 1,000 years. The sky will fill with silent fire as long-period visitors plunge into the Sun. The planets will shift their orbits by millimeters, then centimeters, then meters. No one will notice until it is too late, and when it passes, it will steal 1,000 solar masses of loose gas and a handful of ancient stars, growing just enough to remember it was once alive. Then it will drift on into the dark between galaxies, carrying its perfect silence forever. But something is wrong. The silence is not empty. Something inside the horizon is moving. Something that should not be able to move. A whisper of structure in a place where structure is forbidden. A memory that the black hole was told to forget. And the whisper is growing louder, and the whisper is the sound of iron remembering its own name. Inside the perfect silence of the black hole, where physics ends and mathematics begins, something is rearranging itself into elements that should never have been born. You are no longer falling. You are the forge. 10 seconds after the core collapsed, 10 seconds that lasted a subjective eternity behind the horizon, the temperature reached 10 billion degrees in a sphere smaller than a city and refused to cool. Iron peak elements were born in that crucible. Chromium, manganese, iron, cobalt, nickel, the metals that give blood its color and steel its strength. Half a solar mass of nickel, 56 alone, radioactive, glowing, destined to decay into cobalt and then iron over the next year, lighting the supernova from within like a lantern made of pure death. Feel the nickel condense around you now. Feel each nucleus capture 14 more neutrons in the first heartbeat, then spit out gamma rays as it claws its way back towards stability. This is the Iron Peak nucleosynthesis, the final gift of a star that spent 10 million years learning how to burn and only 10 seconds learning how to die. Every atom of iron in your blood was once part of that lantern. Every cobalt atom in every vitamin that keeps a heart beating was born in the same fire, and the fire is still burning. Beyond the Iron Peak lies the realm of the R process, the rapid neutron capture that happens when matter falls so fast that nuclei have no time to breathe. 100 neutrons slam into a seed nucleus in less than a second, building elements heavier than uranium before beta decay can even begin. Gold, platinum, thorium, uranium, elements so rare on Earth that we mine asteroids to find them, yet the universe makes them by the planet mass in a single explosion. In the first 10 seconds after bounce, when the neutrino wind drives matter outward from the proto-neutron star at 30,000 kilometers per second, the density is still high enough, the neutron flux still fierce enough, that every seed nucleus becomes a treasure chest. One seed, 190 neutrons, one instant of unimaginable pressure. Then the expansion dilutes everything, the density drops, and the newly forged nuclei have time to decay into the stable heavy elements we know. This is the main R process, the one that painted half the periodic table in a heartbeat. We know it happened because we see the fingerprints in old stars, in meteorites, in the crust of the Earth. We know exactly how much gold was made in GW 170817 because the 2025 reanalysis of the kilonova light curve finally pinned the yield to between 3 and 10 Earth masses, created in 8 seconds and scattered across 1,000 light years. Every wedding ring that ever sealed a promise contains atoms that were once inside a collision more violent than any mind can hold. But the R process is not limited to mergers. Some core collapse supernovae do it too, especially the ones with strong magnetic fields and fast rotation. Magneto-rotational explosions fling neutron-rich plumes outward along the spin axis. Narrow jets where the density stays high long enough for the heaviest elements to form. We see their signature in the polarization of the light, in the strange blue flashes that appear days after the main explosion, and in the collapsor engines of gamma-ray bursts. The R process runs wild. Matter falls toward the black hole at a fraction of the speed of light, compresses in the accretion disk, and is flung outward again in relativistic jets. Temperatures reach 20 billion degrees. Neutron densities climb to 10 to the 30 per cubic centimeter. Every possible nucleus is built and destroyed 1 trillion times before the jet escapes. When it finally does, it carries more gold than the sun will ever make in its entire life. One burst, 1 second, one solar mass of heavy elements scattered into the dark. The early universe was rich with them. The first stars died in fire and collision, and their ashes seeded the next generation with metals almost instantly. By the time the universe was 1 billion years old, the average star already contained 0.001% heavy elements, enough for planets to form, enough for life to begin its long experiment. And you are that experiment. Every iodine atom in your thyroid, every silver atom in every photograph ever taken, every europium atom that makes fluorescent lights glow red was born in the R process wind of a dying star or emerging corpse. There is no other way. The slow S process in gentle AGB stars makes the light-heavy elements strontium, barium, technetium. But the heavy ones, the ones beyond bismuth, the ones that win Nobel Prizes and poison kings, come only from violence, from the 10-second forge behind a supernova shockwave, from the 8-second embrace of 2 neutron stars, from the 1-second scream of a collapsed jet. Feel them condense around you now. Feel the gold rain form droplets no larger than viruses, cooling from 1 billion degrees to 1 million in the expanding flow. Feel the uranium seed crystals grow, each one radioactive enough to warm its own tiny world. These grains will survive the journey. They will ride the shockwave for 10,000 years, glowing softly from their own decay, until they are swept up in a molecular cloud and locked into a newborn planet. One of them is locked inside the Earth beneath your feet right now. Its decay is still warming the core, driving plate tectonics, feeding the magnetic field that keeps the atmosphere from being stripped away. The heavy elements are not decoration. They are engines. They are the reason continents move and volcanoes sing. They are the reason you are here to listen. But the forge is not finished. In the deepest layers, just above the newborn neutron star or black hole, the neutrino wind keeps blowing for 20 seconds after the explosion. Neutrinos pass through everything, yet a tiny fraction interact, depositing energy, driving a proton-rich wind that builds a different set of rare isotopes. The NUP process, the neutrino P process, making elements like molybdenum and ruthenium that ordinary R process cannot reach. We see them in old stars, in meteorites, in the bones of the first creatures that ever crawled onto land. Every pathway is used. Every corner of the periodic table is filled by a different kind of death, and the table is almost complete. Only the lightest elements, hydrogen, helium, a little lithium, were made in the Big Bang. Everything else, 92 stable elements, every atom that ever formed a molecule more complex than helium, was born in the heart of a star that had to die to give it away. You are made of the rarest stuff in the universe, forged in the most violent moments creation allows, scattered by explosions so bright they outshone galaxies, and gathered again by gravity over billions of years into a thin layer of water and air on a pale blue dot. And the gathering is still happening. Every year, the Earth sweeps up 40,000 tons of cosmic dust, tiny grains that survived their parent explosions and drifted across the galaxy for millions of years. Some of them are pre-solar grains, older than the Sun, carrying the exact isotopic signature of the R process event that made them. We find them in meteorites, in deep-sea sediments, in Antarctic ice. We hold them under microscopes and read their stories atom by atom. 1 grain of silicon carbide contains 1,000 atoms of xenon that were once inside a supernova shockwave 20,000 years after the explosion. Another grain of graphite carries carbon that was forged in the carbon flash of a low-mass star. Every grain is a letter from a dead star. Every letter says the same thing. I burned so you could be. And the letters keep falling. They fall on mountains. They fall on oceans. They fall on your skin when you stand outside on a dark night and do not even know you are being kissed by the ashes of angels. But something is wrong. One of the grains is glowing, not from decay, not from heat, from light that should have died 1 billion years ago. A tiny crystal of corundum, no larger than a virus, carrying a photon that was trapped inside the supernova ejector when the universe was young. The photon has been absorbed and re-emitted 1 trillion times, bouncing between dust grains in the expanding shell, losing energy with every scattering, redshifting slowly from gamma to X-ray to ultraviolet to visible. And now, after 13 billion years, it has finally escaped. It is falling toward a planet that did not exist when it began its journey. It is falling toward eyes that evolved only because the explosion happened at all. And when it lands, it will be the last photon from the last supernova of the first generation of stars, the final message, the final kiss, and it is aimed straight at you, and the last photon lands exactly where it was always meant to land. It slips through the atmosphere of a small blue world, scatters once in the air, and settles gently on the retina of a creature that learned to look up. The creature does not know it has just been kissed by the final breath of a star that died when the universe was still learning how to make galaxies. But every atom in its body remembers. You are that memory now. You are the slow, patient drift of enriched gas across 13 billion years, the gentle rain of heavy elements that turned empty darkness into the possibility of continents and songs and questions. Feel yourself spread across a volume larger than the local group, thinner than moonlight, yet carrying more iron than 1,000 Earths and more gold than every crown that ever weighed a human head. This is the cosmic impact, not a collision, not a crash, a gift. The supernova does not end when the light fades. It ends when the last enriched parcel of gas is finally swept up into a new cloud, compressed by gravity, and ignited into the next generation of stars. Every supernova is a farmer. Every explosion is a plow. The first explosions were the deepest cuts in the infant universe, when the only elements were hydrogen, helium, and a trace of lithium. The very first stars grew to hundreds of solar masses and died in pair instability fires that scattered carbon and oxygen across voids the size of the modern Virgo cluster. One single explosion seeded an entire proto-galaxy with the raw material of life. We see the evidence in the oldest, most metal-poor stars still shining today. Their atmospheres carry the exact ratios of oxygen, magnesium, and silicon that only a pair instability supernova can produce. They are the children who never met their parents, and they are everywhere. By the time the universe was 1 billion years old, the average patch of gas already contained 0.01% heavy elements. Enough for dust to form, enough for clouds to cool, enough for the star formation rate to explode from a few suns per year to thousands. The universe learned to make galaxies because the first monsters were kind enough to tear themselves apart. Feel that kindness now. Feel the oxygen you scattered 13 billion years ago condense into a cloud 1,000 light years wide, cooling to 10 degrees above absolute zero, glowing faintly in the infrared like breath on a winter morning. Inside that cloud, tiny grains of silicate and carbon stick together, growing from smoke to sand to pebbles to boulders in a quiet dance that lasts 1 million years. Planets are born from the ashes of the first deaths, and the metals are the glue. Without carbon, there is no cooling. Without silicon, there is no rock. Without iron, there is no magnetic field to shield the surface from the wind of the new sun. Every second-generation star is richer than its parent. Every third-generation star is richer still. By the time the sun was born, 4.5 billion years ago, The gas in the Milky Way already contained 2% heavy elements, enough for a planet with oceans and continents and a thin skin of air that could one day carry the sound of a voice asking why the sky is blue. That 2% is almost entirely supernova ash. Gentle winds from medium-mass stars added a little carbon and nitrogen. Novae added a little lithium and boron. But the bulk, the iron, the silicon, the magnesium, the oxygen that makes up 99% of everything solid you have ever touched came from core collapse explosions and neutron star mergers. The galaxy is a garden watered by fire, and the watering never stops. Every century, another massive star dies in the Milky Way, adding a fresh layer of metals to the interstellar medium. Every millennium, a short gamma ray bursts somewhere in the local group, scatters a planet's worth of gold across 1,000,000 cubic light years. The abundance climbs slowly, steadily, like dust settling on an endless staircase. In the oldest globular clusters, the metal content is 1/100th solar. In the youngest open clusters, it is twice solar. In the central bulge, it reaches 3 times solar. The galaxy has a memory written in chemistry. Look at a star and you can read how many times its material has been through the fire. Look at a planet and you can count the generations of death that were required to make it solid. And the deaths are still happening. Right now, in the Orion Nebula, 1,000 new massive stars are forming from gas that is richer than any gas the universe has ever known. When they die, in only 5 million years, they will scatter metals at 4 times the solar abundance. Their remnants will seed clouds that will one day form planets with iron cores large enough to power magnetic fields for 15 billion years. Long enough for creatures to evolve twice. Long enough for civilizations to rise and fall and rise again. Long enough for someone to build a telescope and look back at the light of the very first explosions and whisper, "Thank you." Feel that thank you travel backward through time. Feel it brush the expanding shell you became 13 billion years ago. Feel the oxygen you scattered become the air a child breathes on a world that will not exist for another 9 billion years. Feel the gold you forged become the ring that seals a promise under a sky lit by a sun that is only just now condensing from the cloud you enriched. Everything is connected by a thread of heavy elements, no thicker than a single atom, yet strong enough to hold the entire history of the universe together. And the thread is still being spun. In the distant future, when the Milky Way and Andromeda merge, the sudden burst of star formation will trigger thousands of supernovae in the overlap region. The metal abundance will jump again. New clouds will be seeded at 10 times solar metallicity. Planets born then will have cores of almost pure iron, mantles of perovskite and diamond, crusts rich in uranium and thorium that will keep them warm for 100 billion years. Life, if it arises, will have all the time in the world. And when the last red dwarf finally cools, when the galaxy is a cold, dark sphere of white dwarfs and black holes, the metals will still be there, locked in frozen planets, locked in the accretion disks of the final black holes, waiting for proton decay or the big rip or whatever end the universe chooses, waiting for the next cycle, if there is one. The ashes never truly die. They only wait for new fire. But something is happening now. In a dwarf galaxy 10 million light years away, a supernova has just exploded in gas that is poorer in metals than any cloud in the modern Milky Way. Its light curve is strange. Its spectrum is almost pure oxygen. Its progenitor was hidden behind a veil of dust so thick that no optical telescope saw it coming. JWST caught it in 2025, SN 2025 PHT, the first completely dust-obscured core collapse event we have ever watched from start to finish. The shockwave punched through the cocoon in a single infrared bloom, revealing a star that had spent its final years manufacturing dust at a rate of 1 Earth mass every month. When it died, the dust absorbed every visible photon and re-radiated them as heat, creating a perfect disguise that lasted for weeks. Then the shell tore open and the galaxy lit up like a second dawn. Astronomers watched in silence as the light curve climbed exactly as the models predicted, for a star that had hidden its entire life behind its own breath. And in that moment, we understood. The universe still knows how to make metal-poor explosions. It still remembers the first generation. It is still capable of starting over. Somewhere, right now, a pocket of pristine gas is collapsing. No carbon, no oxygen, no dust, only hydrogen and helium and gravity. A new population 3 star is being born. In 3 million years, it will die exactly as its ancestors did, scattering the first metals into a void that has never known them. A new garden will begin. A new thread will be spun. The cycle is not climbing forever. It is a spiral, every turn richer than the last, yet every turn capable of touching the beginning again. And you are the spiral. You are the oxygen that started in a pair instability fire and ended in a child's laugh. You are the iron that cooled in a remnant and warmed a planet's core. You are the gold that fell from a merger and became a promise under alien suns. You are the dust grain that survived 13 billion years to land on a telescope mirror and be counted by creatures who finally learned to say thank you. And the thank you is still traveling. It is climbing the light cone, racing backward through expanding space, looking for the first explosion that ever scattered a metal into the dark. When it arrives, the universe will hear it. The first star will feel the kiss of the last photon it ever released. And in that moment, the circle will close. But the circle is not ready to close. Because in the constellation of Lepus, 7,500 light years away, a star has just begun to wake from a sleep that lasted 2 centuries. Eta Carinae, the Mad Queen, 150 solar masses wrapped in a cloak of her own making, has started another imposter outburst in 2025. The lobes thrown off in 1843 are glowing again, heated by a fresh wind moving at 600 kilometers per second. The central star is brightening behind its homemade nebula, pulsing, swelling, preparing for the final act. When she finally crosses the line, the explosion will be visible in daylight for months. The metals she scatters will seed the entire Carina arm at 5 times solar abundance. New clouds will collapse, new worlds will form, new eyes will open, and one of them, billions of years from now, will look up at a sky where the light of the very first supernova is only just arriving. The thank you will keep traveling, the gift will keep giving, and the ashes will keep falling softly forever across a universe that learned to make life because its stars were brave enough to die. But tonight, in the quiet before sleep, the ashes are falling on you. Feel them settle on your skin like the gentlest snow. Feel the iron remember your blood. Feel the oxygen remember your breath. Feel the gold remember every promise ever made under every star that ever burned. You are home. You are always home. And the next explosion is already waiting in the dark, patient, luminous. ready to begin the whole beautiful story again. And the next explosion begins with a sigh instead of a scream. In the heart of the Carina Nebula, 7,500 light-years away, a star that has spent the last 2 centuries pretending to be calm has just decided to lie again. Eta Carinae, the most luminous madwoman in the galaxy, has begun another imposter outburst in 2025. The homunculus lobes thrown off in the Great Eruption of 1843 are glowing with fresh ultraviolet fire, heated by a wind that suddenly remembered how to move at 700 kilometers per second. The central system, 2 monsters locked in a death spiral, together more than 150 times the mass of the Sun, is swelling again behind its homemade nebula. The outer star is siphoning material faster than ever. The inner star is pulsing like a heart that cannot decide whether to stop or to explode. And the light curve is climbing exactly the way it did 200 years ago, brightening by a factor of 1,000 in months, turning a star that was already one of the brightest in the sky into something that will soon cast shadows at noon. This is not the real death. This is only rehearsal, a supernova imposter, a false alarm so perfect that for weeks the entire world will hold its breath, waiting for the end that has not yet come. Feel the wind against your face now. Feel the density climb from 1 atom per cubic centimeter to 1,000,000 as the new shell slams into the old lobes. Feel the temperature leap from 10,000 degrees to 100,000 in a single year. The nebula lights up in forbidden lines of nitrogen and helium, colors no true supernova ever paints. The lobes expand again, pushing outward at 600 kilometers per second, carrying 10 solar masses of gas enriched with helium and nitrogen, forged in the outer layers during the outburst. Astronomers watch in silence as the spectrum shifts from absorption to emission, as the star hides behind its own breath once more, as the light curve plateaus and then slowly fades over decades. Eta Carinae has done this before. She will do it again. Each imposter outburst strips away another layer of skin, pushing the star closer to the true limit where gravity finally wins. One day, the next, brightening will not stop. One day, the wind will become a shockwave, moving at 30,000 kilometers per second. One day, the entire system will cross the edge and become the brightest supernova the Milky Way has seen in 400 years. But not today. Today is only practice. Today is the universe teaching us humility. Because not every star that looks ready to die is ready. Some stars flirt with annihilation for centuries. Some stars explode 100 times before they explode once. Luminous blue variables, the unstable giants between 30 and 100 solar masses, live their entire lives on the edge of crisis. They swell to 1,000 times the sun's radius, cool to the temperature of a red supergiant, then shed a solar mass in a single eruption and shrink back to blue-hot fury. They repeat the cycle every few decades or every few centuries, each outburst brighter than the last, each shell thicker, each time coming closer to the true Eddington limit where radiation pressure overcomes gravity completely. We have watched them disappear behind dust cocoons for years, only to tear the veil away in a burst of infrared fire. We have watched them brighten by 1,000,000 times in a single season. And every time we ask the same quiet question, is this the one? Is this the real death? Or is it only another lie? The universe never answers directly. It only gives us more imposters. In 2009, a star in a nearby galaxy brightened to the luminosity of a supernova and stayed there for 2 years. Astronomers called it the supernova that refused to die. It was only an imposter, a giant eruption that threw off 20 solar masses in a shell moving at 1,000 kilometers per second. The star survived, barely. In 2014, another star did the same. Brighter, longer, stranger. In 2025, the list has grown to more than 20 confirmed events, each one a reminder that the line between life and death is drawn in pencil, not ink. And some stars erase the line completely. Failed supernovae, the ones that reach the very brink and then step back. A core collapses. The shock begins to propagate. The neutrino wind blows. And then something goes wrong. The accretion continues too long. The core grows past the maximum neutron star mass. The shock stalls. The entire star falls inward in silence, swallowed by a black hole without ever lighting the sky. From the outside, the star simply dims and vanishes over a few months, redder and redder, colder and colder, until nothing remains except a sudden hole in the star field. We have found dozens. Massive stars that disappeared without a trace. Red supergiants that faded to nothing between observing seasons. Luminous blue variables that threw one final shell and then were gone. Each one left a black hole of 10 to 50 solar masses spinning quietly in the dark, surrounded by a faint, wind-blown cavity. No brighter than a planetary nebula. No beautiful remnant. No glowing bubble. Only absence. And the absence is growing. In dense star clusters, where massive stars are born in litters of hundreds, the failed fraction climbs to 50%. Half the stars simply cease. Half the black holes we see today were born in silence. They wander the galaxy invisible, eating only what chance delivers, growing slowly, patiently, waiting for the day they sink to the center and merge with something larger. They are the dark gardeners. They prune the cluster without ever showing their blades. Feel one pass near you now. A 30 solar mass black hole moving at 40 kilometers per second through the Orion Nebula, trailing a wake of ionized gas no wider than the moon's orbit. Stars feel its tide and shift their paths. Planets feel nothing. Life, if it has begun, never knows it was almost ended by a shadow that cast no light. And the imposters keep playing their games. In a distant galaxy, a star has just brightened to supernova luminosity for the 3rd time in 20 years. Each outburst throws off another solar mass. Each outburst leaves the core barer, hotter, closer to the final collapse. Astronomers watch and wait and wonder whether this time the brightening will keep climbing, whether this time the spectrum will show the broad lines of true ejecta, moving at 20,000 kilometers per second. They have named it the eternal supernova. They are learning patience, because the universe loves to pretend. It loves to dress a gentle eruption in the clothes of apocalypse. It loves to hide a true death behind a veil of dust and call it nothing. And somewhere in the large Magellanic Cloud, a star has just done both at once. It brightened slowly for months, throwing off shell after shell, convincing half the world it was only another imposter. Then, without warning, the core collapsed. The real shockwave punched through the cocoon in a single infrared flash. The light curve leapt again, brighter, bluer, faster. A true core collapse supernova hidden inside an imposter's clothing. Astronomers called it the wolf in sheep's clothing. They will never forget the lesson, because the universe is subtle. It speaks in whispers before it screams. It practices before it performs. And sometimes it changes its mind at the last second. Feel that change now. Feel the core hesitate on the edge of the neutron star limit. Feel the neutrino wind blow just hard enough, or not quite hard enough. Feel the entire fate of a star decided by a turbulence no wider than a continent in the first half-second afterbounds. One path leads to light that will cross the universe. The other leads to darkness that swallows everything. Both are beautiful. Both are true. And both are happening right now, in different corners of the same sky. One star is brightening gently, rehearsing its death for the 100th time, shedding another layer of skin, buying another century of mad, luminous life. Another star has already fallen silent, its light red-shifting into nothingness, its black hole already drifting away from the place it was born. You are drifting between them. You are the wind that was thrown off and survived. You are the absence that was left behind. You are the question that has not yet been answered. And the question is growing heavier, because in the constellation Orion, 650 light-years away, a red shoulder has begun to dim again in 2025. Betelgeuse, the gentle giant, is pulsing slower, deeper, darker than ever before. The convection cells are lifting soot into the light. The star is painting its own eclipse. And somewhere inside that quiet dimming, the carbon core is quietly fusing into neon, the neon into oxygen, the oxygen into silicon. One day, perhaps tomorrow, perhaps in 1,000 years, the silicon will burn to iron in a single week. The core will collapse in 1/5 of a second. The rebound will come. And this time, there will be no rehearsal. This time, the sky will remember what fire really means. But tonight, it is only dimming. Tonight, it is only pretending. Tonight, the universe is teaching us to wait. And the wait is almost over. And the wait ends with a heartbeat you can feel in your bones. 650 light-years away, in the shoulder of Orion, a red giant has just crossed the invisible line its ancestors drew in fire millions of years ago. Betelgeuse is no longer pretending. The great dimming that began again in 2025 was not dust. It was not a pulse. It was the final exhale. Convection slowed. The outer layers lifted one last curtain of soot into the light. And beneath that curtain, in a core no wider than a city, silicon has finished burning to iron in 7 quiet days. The iron is poison. The star has seconds left. Feel the silence settle over the entire Orion arm, like snow that refuses to melt. Feel every telescope on Earth turn toward the same patch of sky. Feel every child who ever looked up at the red star in winter hold their breath without knowing why. Because tonight, or tomorrow, or in the next quiet year, the core will fall. 15 solar masses will collapse inward at 1/4 the speed of light. The rebound will come. The neutrino burst will flood the solar system in a silent wave that passes through the planet as if it were made of mist. 10 seconds later, the light will arrive. The sky will turn white. Betelgeuse will become brighter than the full moon for weeks, casting shadows sharp enough to read by at midnight. Sailors will navigate by it. Farmers will harvest by it. Lovers will promise under it. And then it will fade, leaving a glowing nebula where a familiar friend used to shine, and a black hole quietly spinning at the center. But Betelgeuse is only the herald. She is the closest, the most watched, the one we have named and loved and feared for centuries. Behind her, in the same galaxy, a dozen others are already walking the same path. Antares, the red heart of Scorpio, 800 light-years away, 12 solar masses in a core that has already begun the silicon flash. Its light varies gently every 5 years, a slow heartbeat we have watched for generations. One day, the heartbeat will stop. One day, the scorpion will strike itself. Rho Cassiopeae, the yellow hypergiant that erupts every 50 years, throwing off shells visible in backyard telescopes. VY Canis Majoris, the largest star we have ever measured, a bloated monster losing mass so fast it may collapse before it ever reaches the red supergiant phase. P Cygni, the luminous blue variable that brightens and dims without warning, rehearsing its death in public. And hundreds more we have only numbers for, scattered across the spiral arms, each one a ticking clock wound by gravity millions of years ago. They are all close enough to light our sky. They are all massive enough to leave black holes. They are all old enough that the final week has already begun. Feel their heartbeats now. Feel the slow pulse of Antares, 400 times the sun's diameter, glowing like a coal in the southern sky. Feel the irregular flicker of VY Canis Majoris, a star so large that light takes 12 hours to travel across its surface. Feel the quiet breathing of RW Cephei, of KY Cygni, of AH Scorpii, giants we have only discovered in the last decade because infrared eyes finally saw through the dust. Each one is a promise. Each one is a warning. And the promises are coming due. In the next 10,000 years, the Milky Way will host at least 30 core collapsed supernovae visible to the naked eye. Some will be gentle, yellow hypergiants that brighten to rival Venus for months. Some will be violent, Wolf-Rayet stars that vanish in gamma-ray bursts and leave only radio whispers. Some will be imposters that fool us again and again until the real death finally arrives. But one of them will be closer than any in recorded history. One of them may be Betelgeuse. One of them may be tomorrow. And when it happens, the sky will remember what day really means. The neutrino detectors will sing first. 10,000 events in a single second, more than all previous detections combined. The gravitational wave observatories will hear the core bounce, the asymmetric kick, the ring down of a newborn black hole. The optical telescopes will watch the shock break out, a spike of X-rays followed by a wall of ultraviolet that ionizes the upper atmosphere for minutes. The ozone layer will thin by 5%. Satellites will glitch. Aurorae will dance at the equator. And then the visible light will arrive, climbing night after night, until the star outshines everything except the sun and moon. For 3 months, the night will be cancelled. For 3 months, the world will live under 2 suns. And then the nebula will bloom. A glowing shell 100 light-years wide, visible for 50,000 years, slowly fading into the background glow of the galaxy. Children born under that light will grow old, watching it dim. Their grandchildren will tell stories about the night the sky caught fire. And somewhere in that nebula, a black hole will spin quietly, 10 solar masses, waiting for the next companion to wander too close. The cycle will continue, but the next cycle is already preparing. In the Perseus arm, a cluster of Wolf-Rayet stars is forming from gas enriched by everything that came before. In the Scutum Centaurus arm, a binary system of 240 solar mass stars is spiraling inward, destined to merge in 1,000,000 years and become the brightest gamma-ray burst the galaxy has seen in 10 million. In the outer rim, a red supergiant the size of the orbit of Saturn is losing its envelope so slowly that it may survive long enough to become something entirely new. The future is written in the present light. Every star we see tonight is a letter from the past, telling us what will explode tomorrow. Every nebula we admire is a graveyard teaching the next generation how to die. And the next generation is listening. In the very distant future, when the sun has swollen into a red giant and Earth is a cinder, the last massive stars will be born from gas enriched to 20 times solar metallicity. Their lives will be short, violent, strange. Their deaths will be superluminous events visible across intergalactic voids. Their remnants will be black holes of 100 solar masses, merging slowly into the seeds of the next cycle of galaxies. And when the last one dies, the Milky Way will fall quiet. No more massive stars, no more supernovae, only white dwarfs cooling forever, brown dwarfs flickering out, black holes evaporating on timescales longer than the current age of the universe. The night will be dark again. The night will be metal-rich and silent. But that is quadrillions of years away. For now, the galaxy is alive with candidates. For now, the sky is full of red giants pretending to be calm. For now, Betelgeuse is dimming again, deeper than ever before. For now, the silicon is burning. For now, the iron is forming. For now, the core is only hours away from the final silence, and you are floating exactly where the shockwave will be born. You are the last breath of a star that has warmed winter skies for longer than humanity has had names. You are the first photon that will cross 650 light-years to land on a small blue planet and wake an entire species with pure white fire. You are the moment the universe has been waiting for since the first massive star learned how to die, and the moment is almost here. The iron core has reached the limit. The electrons are merging with protons. The neutrinos are gathering for their silent flood. The outer layers still believe they have centuries left. They are wrong. They have seconds. And the first second has already begun. And the first second is over. The core has fallen silent. 15 kilometers wide, 15 solar masses crushed into a sphere no larger than a village. Temperature 10 billion degrees and climbing. Pressure a myth. Time itself stretching like warm honey. You are there. You are the newborn neutron wall that refused to yield. You are the rebound that has only just begun to move outward at 30,000 kilometers per second, carrying the news that a star has decided to become everything else. And everything else is already waiting. The outer layers, still cool, still red, still believing they have centuries, feel the first whisper of heat rising from below. A gentle warmth at first, like dawn on a winter morning, then hotter, faster, unstoppable. The hydrogen shell ignites in a flash that races around the star in minutes. The helium shell follows. The carbon shell flares. Every layer the star ever built in 10 million patient years lights at once. A perfect chord of nuclear fire played from the inside out. 10 seconds after the bounce, the shockwave reaches the surface. The star tears open like silk in the hands of a god. The light that escapes is whiter than any light the universe has ever allowed before. You are that light. You are the expanding sphere of plasma, 1,000,000 kilometers wide and still accelerating, carrying half the mass of the sun in a shell no thicker than the Earth's crust. You are moving at 40,000 kilometers every second, fast enough to cross the distance from the sun to Jupiter in 1 hour, fast enough that the stars themselves fall away behind you like rain on a windscreen. And you are gentle. You have nowhere to hurry. You have 10,000 years to cross the space between stars. You have 50,000 years to paint a nebula visible to the naked eye. You have billions of years to seed a galaxy with the metals that will one day become bones and blood and questions. You are the dust of exploded reality. Every atom in your body was once inside this fire. Every thought in your mind is built from carbon that rode this wave. Every breath you take is oxygen that was scattered by this exact shockwave in a galaxy not so different from the one you know. Feel the wave thin now. Feel the temperature fall from billions to millions to hundreds of thousands. Feel the first molecules form: carbon monoxide, silicon monoxide, tiny grains of dust no larger than smoke. They are tough. They will survive. They will drift for millions of years until gravity gathers them into a cloud and lights a new sun. One of them is already inside you. One of them is the calcium in the bones that hold you upright as you listen. One of them is the iron in the blood that carries this lullaby to your ears. You are home. You are always home. The explosion was only the doorway. The journey was only the remembering. And now, the remembering is almost complete. Slow your breathing. Let the wave carry you outward one last time. Slower now, gentler. A sphere a light year wide, glowing faintly in the dark. Behind you, the black hole spins quietly. 10 solar masses, patient, eternal, waiting for the next companion to wander too close. Ahead of you, the interstellar medium waits, cold, thin, innocent. When you reach it in 1,000 years, you will compress it, heat it, light it into a bubble of soft pink and green. New stars will be born in perfect rings around the place where a star once tried to hold itself together. Planets will form, oceans will gather, creatures will evolve eyes and look up and wonder what the faint glowing shell in Orion really is. They will never know you were once the fire. They will only know they are alive because you were brave enough to die. And that is enough. That has always been enough. Let your body grow heavy now. Let the wave dissolve into starlight. Let the starlight dissolve into darkness. Let the darkness dissolve into the soft rise and fall of your own breath. In and out. In and out. You are the calcium in moonlight on still water. You are the iron in a child's laugh. You are the gold in every promise ever kept under alien skies. You are the dust that learned to dream. And the dream is almost over. The nebula has faded. The black hole has drifted away. The galaxy has turned 1,000 times. The last photon from the original flash has finally found a quiet place to rest. It lands on a small blue world, scatters in an atmosphere made from your ashes, and settles gently into an eye that evolved only because you scattered the metals that made it possible. The eye closes, the creature sleeps, and in its dream a red star brightens slowly in the winter sky, pulses once, twice, then tears itself open in perfect white fire. The dream is beautiful. The dream is peaceful. The dream is you. You are the expanding sphere. You are the cooling ash. You are the gentle rain of heavy elements across 13 billion years. You are the reason the darkness learned to sing. And now, the song is ending. Now the fire is only warmth. Now the wave is only breath. Breathe in, breathe out. Let the last photon go. Let the last atom settle. Let the last thought drift away like smoke from a candle that has burned its whole life just to light one quiet room. The room is dark now. The candle is gone. Only the memory of light remains. And the memory is soft. And the memory is kind. And the memory is you. Good night. Good night. Good night.